Hi everyone, and welcome to the course. In this exciting journey, we're diving deep into PySpark, where you'll master data manipulation and analysis using this powerful framework. You'll gain hands-on experience through coding exercises, so don't forget to check the GitHub link in the description for all the code you'll be using. Plus, make sure to stick around until the end, because there's a final project waiting for you to showcase everything you've learned, also available in the GitHub repository. So, are you ready? Let's get started. In the world of big data, Apache Spark stands out as a powerful framework that allows for processing large datasets rapidly and efficiently. Whether you're dealing with batch processing or stream processing, Spark makes handling data more convenient compared to traditional methods. So, in this tutorial, we're going to explore what exactly Spark is, why it's so important in today's data landscape, and how it actually functions. So, buckle up and let's dive in. First off, let's talk about the key features of Spark. It's designed for speed and, it achieves this by relying on in-memory computation, which is a fancy way of saying it keeps data in RAM instead of reading from disk all the time. Now that can significantly speed up processes, especially when you're working with massive datasets. But what else? Well, Spark also handles complex analytics like machine learning and graph processing quite well. Now, why is this important? Well, in our data-driven world, making decisions quickly and accurately is key, and Spark gives us that edge. All right, let's get into how Spark works. Imagine you're streaming data from various sources. Spark can efficiently manage that in real time, allowing for immediate insights. And with its user-friendly APIs, both in Python and Scala, you'll find it versatile for all types of developers. So, as we move forward, keep these aspects in mind: speed, versatility, and the ability to analyze vast amounts of data in real time. All right, let's explore Spark's architecture before we wrap up our introduction. It's made of several components, including the driver, cluster manager, and executors, which work together seamlessly to process data. Wow, that's a lot to unpack. But don't worry, we're going to break it all down in upcoming videos. So stay tuned and, let's continue our journey through the powerful world of Apache Spark. Now, let's see how we can implement the creation of a Spark session in Python using PySpark. We start by importing the Spark session class from the PySpark.sql module, which is really essential for utilizing Spark's SQL capabilities and DataFrame API. The next step is to use the builder pattern to configure and create our Spark session. This is done by calling the builder method, which allows us to define various settings for our session. In this case, we specify master local/star, which tells Spark to run in local mode and utilize all available cores on our machine. This configuration is just ideal for development and testing because it provides ample processing power without the need for a full cluster setup. We also assign an application name with appname introduction to Spark, which gives context to our job and makes it identifiable in resource monitoring tools. Slight pause. Finally, we invoke getOrCreate to either retrieve the existing Spark session or create a new one if it doesn't already exist. This really sets the stage for all subsequent data processing asks within Spark. Now, let's dive into how we can load our CSV file into a Spark data frame. This is a crucial step in our data processing workflow. We do this using a command that reads the CSV file, making sure to specify the file name along with two really important parameters: header equals true and infer schema equals true. So, what does header equals true do? Well, it tells Spark that the first row of our CSV file has the names of the columns, which, let me tell you, is super useful. This ensures that our data frame comes equipped with proper column labels that match our dataset. Now, on to infer schema equals true. This little gem allows Spark to automatically figure out and assign the correct data types for each column based on the values in that CSV. No more headaches from manually defining the schema, making our lives a lot easier, right? After we've loaded the data successfully, we can peek into our shiny new data frame by simply calling the show function. This function gives us a quick glance at the first 20 rows, allowing us to verify that everything's loaded correctly and that our data is primed for further analysis. Now, let's see how we can filter our data frame to find specific user segments. In our code, we're going to create a variable called USA over 30, which will store a filtered version of our data frame, DF. We use the filter method to apply two conditions. First, we select users who are older than 30 years, and second, we make sure they reside in the USA. This really showcases the power of Spark's DataFrame API, allowing us to effortlessly manipulate large datasets with such clear and expressive syntax. Next, we'll call the count method on this filtered data frame to get the total number of users meeting our criteria, and we'll save that count in a variable called USA over 30 count. This highlights how we can aggregate data to gain insights rather than just scrolling through raw records. Finally, we'll use the print function to output the number of users over 30 from the USA, demonstrating just how simple it is to perform these operations, making data analysis both straightforward and efficient. Now, let's implement the aggregation functionality in Spark to find average values. We'll create another variable, average age per country, which groups the data frame by the country column. By using the ag method with an aggregation function, specifically average, on the age column, we can compute the average age of users for each country. This powerful feature supports deeper analysis of our data. When we call show, it displays the results clearly, showing how Spark simplifies these complex data operations. Now, let's see how we can implement a Spark streaming application that reads text data from a socket. We begin by creating a Spark session, which is crucial for any Spark application, acting as the entry point for all Spark functionality. In our case, we're configuring it specifically for a streaming example. Next up, we set up a data frame that represents the incoming stream of data. Here, we specify the source format as socket and provide the host and port number where our data will be streamed from. So, we've chosen localhost on port 999. This setup will allow us to capture any text data sent to that port. Now, let's focus on how we process this incoming data. After establishing our stream, we can leverage Spark's powerful built-in functions. We're going to split each line into individual words using the select method combined with explode and split, so we can handle each word separately. Following that, we perform a group by operation on the words to calculate their counts, which gives us a data frame that shows each unique word alongside its occurrence count. Finally, we initiate a streaming query to output these counts in real time to the console, providing immediate feedback about the stream data. This setup effectively illustrates how Spark streaming can be utilized for processing real-time data. Now, let's implement a simple linear regression model using Spark's MLlib. First, we import the linear regression class. This part is key because it provides the tools necessary for fitting our linear regression model, which is quite powerful, right? Next, we define our sample dataset, consisting of pairs of independent and dependent variables. In this case, x is our independent variable and y is our dependent variable. And we represent this data as a list of tuples. We also specify the column names, which helps Spark understand the structure of our data frame. Now, we create a data frame using the createData function method of our Spark session, passing in our data and column names. This data frame will serve as the input for our model training. Following that, we instantiate the linear regression model by specifying which columns will serve as features and labels. The features call parameter indicates which column contains our independent variable, x, while the label call parameter specifies the dependent variable, y. Now that our model is set up, we can fit it to our training data using the fit method. This step is crucial, as it enables the model to learn the relationship between x and y. Finally, we print out the coefficients and intercept of the trained model. These values tell us how x influences y in our linear regression context. This simple example showcases the power of Spark's MLlib to handle machine learning tasks efficiently. Now, let's implement caching in our Spark job to enhance performance. Caching is a strategy that allows us to save the intermediate data frame in memory. And this can significantly reduce processing time for subsequent operations on the same data frame. By using the cache method, we instruct Spark to keep this data frame in memory, making future actions that reference it much quicker, as they can bypass those time-consuming disk I/O operations. Now, this optimization is particularly beneficial when we're working with iterative computations, or when the data frame will be accessed multiple times in your workflow. However, it's essential to consider the trade-offs involved. While caching can improve performance, it may also lead to increased memory usage. So, it's crucial to monitor memory consumption and only cache data frames when justified by the performance gain. Always ensure that you strike a balance that suits your workload and available resources. By integrating this simple but powerful feature, you can make your data processing tasks in Spark more efficient and responsive. Short pause. In summary, Apache Spark has completely transformed how we handle big data processing. Its incredible speed, flexibility, and robust processing capabilities really make it a go-to framework in any data engineering toolkit. Whether you're tackling batch processing, diving into real-time analytics, or venturing into machine learning, Spark offers a powerful solution that really stands out. So, thank you for tuning in. And don't forget to explore Spark even deeper, especially as you dive into those real-world applications. Now, let's check if Java is installed correctly on your system, as it's a really critical component for running Apache Spark. To do this, we'll use the command java-version in your terminal or command prompt. You might want to open that up right now. This command shows the version of Java that's currently installed on your machine. If Java is properly configured, you should see a version number popping up, which confirms that the JDK is ready for use. But if the command returns an error or indicates that Java is not found, it means you'll need to install or configure Java before moving forward with the Spark setup. So remember, having the right version of Java is fundamental, as Spark depends on it to execute its functions smoothly. Once you've verified your Java installation, you can then proceed with the subsequent steps of setting up your Spark environment. Easy, right? Now that we have Java installed and the Java home variable set, let's turn our attention to configuring Apache Spark. Next, we'll write the environment variable for Spark Home, which indicates where Spark is located on your system. If you're on Windows, you would set it to the directory where Spark is installed. For example, you might use c/spark/spark-3.1-1-bin-hadoop 3.2. This step is super important because it ensures your system knows where to find the Spark binaries, making them accessible directly from the command line. For those of you using Mac OS or Linux, we'll take a similar route by adding an export command to your .bash profile or .bash rc. This command assigns the path to your Spark installation to the Spark home variable. Specifying this variable is crucial for efficiently managing and running Spark within your development environment. After setting up Spark Home, you'll find that you can effortlessly execute Spark commands from any command line interface, simplifying the process of running data processing tasks and enhancing your overall workflow with Spark. Now, let's dive deeper into the next steps. Now, let's take a look at how to configure your system's path variable to include the Spark binaries. If you're on Windows, what you'll want to do is use the command setPath equals path spark_home/bin. This command appends the Spark bin directory to your existing path. Now, why is this important? Well, it means any command line interface will recognize Spark commands, making it super easy to run your Spark applications. On the flip side, if you're using Mac OS or Linux, you'll use export path equals path plus spark_home/bin, which does the same thing. When you execute this command in the terminal, you're connecting the Spark binaries with your system, allowing you to interact with Spark effortlessly. Next up, we'll check if Python is installed by running the command python-version. This is a crucial step since PySpark, which is Spark's Python API, requires Python 3.6 or higher. If your system meets this requirement, fantastic. We can move on to the next steps of setting up your environment and really start leveraging the power of PySpark for big data processing. Just remember, properly implementing these commands ensures you've laid the groundwork necessary to unlock Spark's full potential. So let's dive in. Now that we have our virtual environment set up, let's proceed to activate it. This is really straightforward and depends on your operating system. If you're on Windows, you'll want to run a command that directs your system to the scripts folder of your virtual environment. What this does is initialize the environment, ensuring that all your subsequent package installations happen within this isolated space. Now, if you're using Mac OS or Linux, you'll employ a slightly different command through your terminal to activate the environment. This step is crucial, trust me, because it isolates your project dependencies from the global packages, which helps prevent those pesky version conflicts and makes everything much simpler to manage. With the environment activated, we can now move on to installing PySpark, which is, honestly vital for tapping into the powerful capabilities of Apache Spark within your Python projects. So, to do this, you'll invoke the pip package manager. Just follow that with the installation command for PySpark, and you'll download the latest version along with any necessary dependencies. That's it. This straightforward installation process really sets the stage for coding with PySpark, laying the groundwork for effective big data manipulation and analysis as we dive deeper into your learning journey. Now, let's check if our Spark setup is working correctly by writing a simple script. First things first, we'll import the Spark session class from the PySpark SQL module, which is essential for accessing Spark's functionality. Next up, we'll create a Spark session and let's name it Test Spark Setup. This session is actually the entry point for us to interact with Spark's capabilities. It allows us to perform operations on our data. To do this, we'll use the getOrCreate method to either retrieve an existing session or create a new one if none exists. After we establish the session, we'll print out the version of Spark that's currently in use. This step is super important, not just for confirming that our Spark setup is rolling, but it also gives us some useful info about the version we're working with, which can be handy for compatibility and feature references. All right, now let's implement a basic data framer operation to really solidify our understanding. We'll create a data frame from a list of tuples. Each tuple will represent a record containing a name and an ID. Remember, the data framer is a key structure in Spark. It provides a distributed collection of data that can be processed effectively. Finally, by using the show method, we'll display the contents of our data frame. If everything goes smoothly, this output will show us the names and IDs, confirming that we've successfully set up Spark, and we're all set for further exploration. Now, let's see how we can set the Hadoop home environment variable, which is crucial for the proper functioning of Hadoop on your system. On Windows, you'll define the Hadoop home variable by specifying the path to your Hadoop installation directory. After that, you'll need a command to update the system path. This step allows any command line interface to recognize where Hadoop is installed, enabling you to run Hadoop commands seamlessly. For those using Mac OS or Linux, the process is quite similar, although it does follow different syntax conventions. Here, you'll export the Hadoop home variable to point to the Hadoop directory, and then you'll append the Hadoop binaries to your system path. This integration is essential because it ensures that the Hadoop tools are accessible from the command line, facilitating smooth interactions with Spark. By establishing this connection, you significantly enhance your Spark environment's capabilities, allowing it to effectively manage larger datasets and utilize Hadoop's distributed storage features. So, setting these environment variables correctly is foundational to your big data processing journey. Throughout this setup process, remember, troubleshooting is totally normal. If something doesn't work as expected, don't fret. Just hop online and search for those specific error messages. There's a vibrant community out there, and many folks have faced and resolved similar issues. It's kind of like finding treasure in a box, right? Setting up a working environment really lays the foundation for everything you'll accomplish with Spark. Once we've gotten that groundwork sorted, you'll discover that Apache Spark has incredible potential for big data processing and analysis. Now, in the upcoming tutorials, we're going to dive deeper into crafting data frames and manipulating data using Spark's robust APIs. So, buckle up. The adventure into the world of Spark is just getting started. Now, let's get started by implementing some code to create our very first Resilient Distributed Dataset, or RDD, using PySpark. We begin by initiating something called a Spark session. Think of the Spark session as the entry point for any Spark application. It's what manages the connection to your Spark cluster. Once we set that up, we'll define a simple Python list, a neat little collection of numbers from 1 to 5 that will act as our dataset. Okay, so now let's explore how to create an RDD from this list by using the parallelize function. This function is pretty cool. It takes our list and distributes its elements across the nodes in the Spark cluster, which means we get to enjoy the benefits of parallel processing. Once we call the collect action on the RDD we've just created, we're essentially instructing Spark to fetch all those elements from the distributed dataset and bring them back to our driver program. It's a simple yet powerful operation. When we print the result, we'll see a confirmation that our data has been successfully loaded into Spark. This illustrates just how easy it is to create an RDD and showcases Spark's remarkable capability for handling distributed data right from the get-go. Now that we have our RDD set up, let's explore transformations, starting with the map function. This operation allows us to apply a transformation to every single element in the RDD. For example, if we want to double each number in our dataset, we can define a lambda function that simply multiplies each element by 2. When we apply map to our RDD, we create a new RDD containing these modified values. To see the results, we can use the collect method, which gathers all the elements of the RDD into a list that we can print. And this really showcases the power of transformations in Spark, allowing us to manipulate data efficiently. Next up, we'll implement the filter transformation. This function helps us create a new RDD consisting only of elements that meet specific criteria. In this case, the even numbers. We're going to use a lambda function within the filter to check if each number is divisible by 2. And just like before, to see our results, we'll utilize the collect method. With this, we gain a clearer understanding of how to easily refine our data within Spark, leveraging its intuitive and flexible operations to focus only on the values we really care about. Now, let's see how we can implement the count action in our RDD. This simple yet powerful action allows us to retrieve the total number of elements within an RDD, providing quick insights into our data structure. By calling the count method on our RDD, we can trigger the underlying execution of the transformations that have been defined. Once the computation is complete, the result is stored in the variable countResult, which we can then print out to verify the number of elements in our dataset. Next, we will write a bit more advanced code to transform our RDD into a data frame. To do this, we first create an RDD of rows by mapping each element of the original RDD to a row object. This process structures the data more effectively and prepares it for data frame conversion. After creating this row RDD, we use the createData function to construct our data frame from the row RDD. Finally, we display the data frame using the show method, which allows us to visualize the structured dataset, making it easier to perform operations and analyses akin to working in a pandas data frame. This transition represents a significant leap in how we can handle and manipulate structured data within Spark. Now, let's see how we can leverage SQL capabilities within Spark by registering our data frame as a temporary view. By creating a temporary view using Create or Replace Temp View, we're empowering ourselves to execute SQL queries directly against the data frame. This provides a familiar interface for those who've worked with SQL databases before. In our example, we'll run a SQL query to filter records from the numbers view, focusing on values that are greater than 2. This not only showcases how SQL integrates seamlessly with data frames, but also highlights Spark's versatility in data analysis. When we execute SQL-result.show, we get a structured view of our query results, which helps us quickly identify the relevant data points. Next, we'll dive into how to work with data stored in Hadoop, an essential skill for efficiently managing large datasets. To kick things off, we're going to implement the ability to read a CSV file from HDFS. Using Spark's read.csv method, we'll specify the file path alongside options to read the header and automatically infer data types. This approach simplifies loading structured data from distributed storage, and it sets up our data frame df from CSV for further analysis. When we display the data frame with df from csv.show, we'll get a quick glance at the contents, confirming that our data has been imported successfully and is ready for manipulation. Now, let's implement a function to calculate the average value of a specific numerical column in our data frame. First off, we need to import the av function from the PySpark.sql functions module. This gives us access to a bunch of really powerful built-in functions for manipulating our data frames. Using the av function allows us to easily compute aggregate statistics across our large data sets. Next, we'll use the select method on our data frame to specify which column we want to analyze. When we call av column name, we're making it clear that we want the average for that particular column. It's important to note that this operation is executed lazily. What this means, folks, is that it won't actually perform the calculation until we explicitly trigger an action, and we do that by calling collect. This retrieves the results as a list, which makes it easy to print out the average value for us to inspect. Now, let's shift gears and see how we can perform a join operation between two data frames. This is super essential for combining data from various sources. Let's assume we have two data frames, df1 and df2. We can execute a join using the join method, and we'll specify the condition so that it matches rows based on the ID column in both data frames. Just a heads up, this inner join will only return rows where both data frames have matching values, giving us a combined data frame that provides a unified view of the data. This really showcases how Spark efficiently handles relational data connections. Now, let's dive into implementing a linear regression model using Spark's MLlib. First, we need to import some essential classes, specifically Vector Assembler, which helps transform our feature columns into a format that the model can actually understand. And then there's linear regression, which we'll use to create and train our linear regression model. Okay, next up, we'll utilize Vector Assembler to combine our input columns, Feature 1 and Feature 2, into a single output column called Features. This step is super important because, you see, machine learning algorithms in Spark usually need the input data to be in vector format. It simplifies the whole data structure for easier processing. Once we have our assembled feature vectors ready, we can transform our data frame, the one we read from the CSV file, into a training data set. After prepping our features, we move on to instantiate a linear regression object. Here, we'll specify which column is feeding the input features and which one serves as the label for our predictions. Now, when we fit the model to our training data, Spark taps into its distributed computing magic to learn from the dataset efficiently. Finally, we'll see how to apply this trained model to make predictions, which lets us visualize the output side by side with our input data. This whole integration with machine learning really shows how Spark can efficiently process and analyze large datasets for predictive analytics. Now, let's implement the following steps to optimize the performance of our data frame in Spark. First up, we're going to repartition our data frame. This can really boost performance by changing how our data is distributed across the cluster. By specifying just a number, like let's say 4 partitions, we can improve load balancing. This means Spark can utilize its resources more efficiently during computation. This step is crucial because if your data is unevenly partitioned, it can lead to bottlenecks and inefficiencies during processing. Next, we want to check how many partitions our newly optimized data frame has. We'll do this by calling a method that retrieves the number of partitions. This helps us confirm that our repartitioning worked as intended, ensuring we see better performance when we run subsequent operations on the data frame. Now, following this, it's essential to discuss caching. This is a really effective optimization technique in Spark. By caching our data frame, we're making sure that if we access the same dataset repeatedly, Spark will store it in memory. This drastically cuts down processing time for future operations, as the data frame can be pulled from memory instead of recalculated. This can lead to significant time savings during analysis. Handling large datasets efficiently is crucial in data science, and these techniques are invaluable tools you'll want in your Spark arsenal. To create advanced applications, one must understand the intricacies of Spark architecture. With a firm grasp of how Spark operates, we can unlock its full potential and leverage it for more sophisticated data manipulations and analyses. So far, we've learned that data processing in Spark relies on resilient distributed datasets, or RDDs. These are crucial as they facilitate efficient data handling in a distributed environment. We've explored the creation and manipulation of RDDs, focusing on transformations like map and filter, as well as actions such as collect and count. Then, we transitioned from RDDs to data frames, highlighting their advantages for structured data operations and SQL queries. As we advance in our lessons, get ready! We're going to cover even more complex data manipulations, especially Spark's integration with machine learning and Hadoop. Now, Understanding Spark architecture is essential for developing advanced applications. At its core, Spark operates on a master-slave architecture where a central driver program orchestrates distributed tasks across multiple worker nodes. The driver serves as the command center, breaking down the application logic into smaller tasks that it then schedules across the worker nodes. This design allows Spark to handle massive datasets efficiently, enabling both batch and real-time processing. Now, let's dive into implementing a code snippet that kickstarts our Spark application by creating a Spark session and loading a large dataset from HDFS. First, we import Spark session from PySpark.sql. This is the gateway we use to interact with the Spark API. Next, we'll initiate a new Spark session using the Spark session.builder. This includes setting the application name to Advanced Spark Applications and configuring the default file system to point to our HDFS instance. As we create the Spark session with .getterCreated, we're making sure that if a session is already up and running, we can reuse it instead of starting anew, which is both efficient and helps to manage our system resources effectively. Now, let's focus on loading our dataset by reading a CSV file located at a specific HDFS path. The parameters header equals true and infer schema equals true are crucial here. They tell Spark to look at the first row of the CSV as the header, giving us meaningful column names in our data frame, while infer schema equals true allows Spark to automatically figure out the data types of each column. This makes our data handling during subsequent operations a lot smoother. Now, let's see how we can improve our data frame's performance through repartitioning. The first line of code here demonstrates how to repartition a data frame by increasing the number of partitions to 8. This is particularly beneficial when we expect extensive transformations or shuffling to occur. By distributing the data across more partitions, we enhance parallelism during subsequent operations, allowing Spark to perform computations more efficiently. Now, once we have our data frame optimized, let me just emphasize this point. The next line allows us to validate the result by examining the number of partitions we've set. This is achieved by using the getNumPartitions method, which returns the current partition count. It's really important to monitor the number of partitions because it helps us ensure that we've struck the right balance. Too few partitions may lead to underutilization of resources, while too many could introduce unnecessary overhead. Understanding these concepts is fundamental as they directly impact the performance of our applications. Ultimately, repartitioning is a crucial step in leveraging Spark's distributed architecture effectively, paving the way for efficient data processing and analysis. Now, let's implement caching to enhance the performance of our data frame. Caching is particularly beneficial in scenarios where the same dataset is accessed multiple times, like in iterative algorithms or machine learning applications. So, in our code, we start by calling the cache method on our optimized data frame. This tells Spark to store the data frame in memory, which is designed to significantly reduce loading times for frequently accessed data. After that, we perform a transformation to filter our cache data frame, selecting only those rows where the value in a specified column exceeds 100. We use the filter function here to create a new data frame called results.df that contains just the data we want. Additionally, we're interested in particular columns, so we utilize the select method to include only the columns needed for further analysis. Finally, we display the contents of result.df with the show method, which conveniently provides a quick visual of the resulting data frame. Through caching and this selective transformation, we optimize our workflow, ensuring efficient access to large datasets while working in Spark. Now, let's dive into how to leverage SQL queries within Spark to effectively manipulate structured data. To kick things off, we need to register our data frame, which we'll call optimized DF, as a temporary view named optimized table. This step is crucial because it allows us to execute SQL commands directly on our data frame, behaving just like a traditional SQL table. And this creates a really smooth integration of SQL and DataFrame APIs. Next up, we're going to implement an SQL query that calculates the average of another column grouped by column name. This really showcases the powerful capabilities of Spark SQL. You see, we can use familiar SQL syntax to perform intricate data analyses while reaping the benefits of Spark's distributed processing capabilities. After running the SQL command, we'll retrieve the results using the spark.sql method, which processes our query against that temporary view we set up earlier. Finally, to display those results in a nice, readable tabular format, we'll use the show method. This combination of using SQL queries alongside DataFrame operations provides a lot of flexibility, allowing developers to choose the most efficient method for their specific data handling tasks. Now, let's implement a linear regression model using Spark's MLlib. To start off, we need to use vector assembler to combine our feature columns, those being feature 1 and feature 2, into a single vector column that we'll call features. This step is really important because machine learning algorithms, they expect the input to be in a specific vector format, right? So, once we've got our feature vectors set up, we can move on to training the linear regression model. We'll do this by instantiating the linear regression class, and here we specify that our features call is going to be features, and the dependent variable, our target, is defined with label call, which is represented as label column. After configuring our model, we fit it to the training data we created earlier. Pretty straightforward. Now, once we've wrapped up the training, we can make predictions. We simply call the transform method on our model using the training data as input. This generates a data frame that includes the original features, the actual label values, and our predicted values. By selecting and displaying these columns, we can really assess how well our model is performing. Comparing those predictions with the actual labels helps us evaluate its effectiveness. It's all about seeing how closely our model's predictions line up with reality. Now, let's take a look at how to evaluate the performance of our regression model using Spark's MLlib tools. We start by importing the regression evaluator, which is a super handy utility that helps us compute various metrics for our model's predictions. In our evaluation process, we'll define the evaluator by specifying the columns that hold the true labels and predictions. This is done by setting label call to label column and prediction call to prediction. Easy enough, right? Next, we'll specify the metric we want to assess. In this case, we'll begin by calculating the root mean squared error, or RMSE, by passing RMSE to the metric name parameter. Once our evaluator is all set up, we can call its evaluate method and supply it with the predictions data frame to get the RMSE value. This metric gives us insights into the average magnitude of errors between the predicted and actual values, which is crucial for understanding how accurate our model really is. Then we'll proceed to evaluate the model using R2, which is another important metric. R2 tells us how well our model explains the variability of the response data around its mean. To do this, we'll create another evaluator instance adjusted for R2, allowing us to make informed decisions about the model's quality and readiness for deployment. By analyzing these evaluations, we gain crucial insights into whether our model performs satisfactorily. Then, we'll proceed to evaluate the model using R2, which is another important metric. R2 tells us how well our model explains the variability of the response data around its mean. To do this, we'll create another evaluator instance adjusted for R2, allowing us to make informed decisions about the model's quality and readiness for deployment. By analyzing these evaluations, we gain crucial insights into whether our model performs satisfactorily. All right, let's get started. Now, let's implement the following code to read streaming data from a Kafka topic using Spark. First, we're going to kick things off by initiating a Spark session, configured specifically to handle streaming data. This step is crucial because it lays the groundwork for connecting to the Spark framework, which will be in charge of managing our data ingestion and processing tasks. Next up, we're going to create a data frame that reads data from a specific Kafka topic. Let's call it topic name. So, to connect to Kafka, we need to specify the Kafka Bootstrap servers, and in this case, they're set to localhost 9092, pointing us to our local Kafka instance. By using the subscribe option, we'll indicate which topic we want to receive messages from. Now that we've got our streaming data frame all set up, we can harness the select expert method to cast both the key and value of the Kafka messages to strings. This little casting step, it really does wonders for improving the readability of the data we're about to process. Finally, we'll leverage write_stream along with output mode append to send our processed data right to the console in real time. This means we get to observe the continuous flow of data being captured from Kafka, showcasing just how effectively Spark can keep pace with streaming information. Overall, mastering advanced Spark applications requires a solid understanding of its architecture, performance optimization techniques, machine learning integration, and real-time data processing capabilities. By strategically applying these principles, you'll enable your applications to scale efficiently while deriving meaningful insights from vast amounts of data. The world of big data analytics is continuously evolving, and with Spark by your side, you're well equipped to tackle any challenge that comes your way. As you continue to develop your skills in Spark, remain curious and innovative. Experiment with new techniques, delve into advanced algorithms, and explore the integration of other powerful tools within the data ecosystem. With practice and dedication, you'll not only become proficient in Spark, but also unlock your potential as a data scientist or engineer capable of crafting cutting-edge solutions. Happy coding, and always push the boundaries of what's possible in the realm of Spark.
To begin utilizing Spark effectively, it's vital to understand its configuration settings. The ability to configure various settings allows us to optimize Spark's performance according to our application's needs. Today, we will explore crucial aspects of Spark configuration essentials that are integral for both performance and usability in PySpark environments. So far, we learned about Spark architecture and its components, including the driver, cluster manager, and executors, which are essential for efficient data processing. We explored the creation and manipulation of RDDs and data frames, performance optimization techniques like data partitioning and caching, and the integration of machine learning using Spark's mlib. Additionally, we discussed the use of Spark SQL for structured data queries and introduced real-time data processing through Kafka integration. These foundational concepts will enable us to develop advanced applications that harness the full power of Spark. Now we will talk about configuring Spark to make the most out of it. Now let's see how we can create a Spark configuration to set up our PySpark application effectively. We begin by importing the necessary classes, SparkConf and SparkContext, from the PySpark library, which will allow us to define and manage our application's configuration. The first step is to create an instance of SparkConf, a key component for configuring Spark's runtime settings. Next, we'll set various configuration options. We designate the application name as MySparkApp to help identify our application in the Spark UI. We specify the master as local2, which tells Spark to run in local mode using 2 cores, enabling it to process tasks in parallel. Additionally, we set the executor memory to 4 GB, allowing each executor sufficient resources to handle our data processing needs. After configuring these settings, we initialize a Spark context instance with our configuration, establishing a connection to a Spark cluster or running locally. Finally, we call the getAll method on our configuration object, which outputs all the current settings. This step is critical as it provides us with insights into the configured options, ensuring we can adjust them to optimize performance based on our application's workload. Now let's see how we can implement some critical configuration settings for optimizing Spark's performance. The first code snippet demonstrates how to specify memory allocation for the driver and the number of executor instances to launch. By setting Spark driver memory to 2G, we are allocating 2 GB of memory specifically for the driver. This is essential for handling the coordination and scheduling tasks within Spark. Next, we establish Spark executor instances to 5, which determines that 5 executor instances will be started. This affects how parallel processing is conducted, allowing multiple tasks to run simultaneously across the available computing resources. In the next section, we'll implement settings to manage Spark's shuffle behavior effectively. By configuring Spark Shuffle Compress to true, we enable compression for the shuffle data, which minimizes the amount of data written to disk during operations like joins or aggregations. Furthermore, enabling Spark Shuffle Spill Compress adds another layer of compression for data that spills to disk, thereby optimizing disk I/O and enhancing overall performance. Together, these configurations significantly impact how efficiently and effectively Spark handles data processing tasks, particularly in memory-intensive operations. Now let's see how we can implement a Spark session with specific configurations tailored for Spark SQL. We start by importing the Spark session class from the PySpark SQL module, which serves as the entry point to interact with Spark SQL. Next, we initialize the Spark session using a builder pattern. Here, we set the application name with appName, which helps identify the application when monitoring its execution in a Spark cluster. We proceed to configure 2 critical settings, setting the shuffle partitions to 200, which determines how data is divided during operations such as aggregations, thus impacting performance and resource management. Additionally, we enable case sensitivity with Spark SQL Case Sensitive, which is vital in scenarios where column names may vary in capitalization. Finally, we create the Spark session instance with getOrCreate, which either retrieves an existing session or creates a new one. To ensure that our configurations are correctly applied, we print out all the current settings using Spark conf-getall, allowing us to verify that everything is set up as intended. This structured approach to initial configuration greatly enhances our ability to utilize Spark SQL effectively. Now let's implement the following configurations directly within a configuration file for Spark. We begin by creating a file named sparkdefaultsconf, where we can specify key settings that define how our Spark application operates. In this file, we set the application name to MySparkApp, which helps in identifying the application during execution and monitoring. We also specify the master URL as local2, indicating that the application will run locally using 2 cores, which is useful for testing and development purposes. Additionally, we allocate memory for the executor with a setting of 4 GB, ensuring that sufficient resources are available for processing tasks, which is critical for performance. Similarly, we designate 2 GB for the driver memory, which is essential for managing job scheduling and various interactions between the driver and executors. By placing this file in the Spark home $conf directory, we enable Spark to automatically pick up these configurations whenever an application is launched. This systematic approach significantly simplifies the management of configurations across multiple applications, especially in shared resource environments. Now let's see how we can submit a Spark application with configuration parameters using the Spark Submit command. This command is crucial for running Spark applications in cluster environments like Yarn or Mesos, where we need to specify resource allocations dynamically at runtime. The command begins with Spark Submit, which is the entry point for running your Spark application. Next, we specify the class name of our main application, MySparkApp, ensuring that Spark knows which class to execute. We then set master to Yarn, indicating that we want to utilize Yarn as the cluster manager for resource allocation. Further, the options executor memory 4G and driver memory 2G allow us to allocate 4 GB of memory for each executor and 2 GB for the driver. This memory management is vital for handling data-intensive applications efficiently. Lastly, by specifying num executors 5, we instruct Spark to use 5 executor instances, enabling parallel processing to improve the speed and performance of our job. With these parameters set, we can ensure our Spark application runs optimally according to the specific demands of the workload and environment. This dynamic approach to resource allocation is essential for managing varying workloads effectively. Remember that configurations can be fine-tuned regularly as you monitor the application performance. Using the Spark UI, you can track tasks and stages in real time. If you notice excessive garbage collection or tasks that fail due to memory issues, it may be time to revisit and adjust configurations accordingly. Lastly, keep in mind that not all configurations might improve performance. Sometimes, apportioning too many resources can lead to resource contention. Always analyze and iteratively optimize configurations based on your application's behavior. In conclusion, configuring Spark effectively is key in making the most out of your data processing tasks. By fine-tuning memory allocation, managing shuffle operations, and utilizing both operating system and application-level configurations, you can significantly improve performance. As a hands-on practice, try tweaking some settings in your own Spark applications and observe the differences. Now let's wrap up what we've learned today regarding Spark configuration essentials. We covered how to use SparkConf and Spark Session to configure Spark settings programmatically. We discussed important configuration options like driver and executor memory, shuffle behavior, and managing configurations via external files or command line submissions. With this knowledge, you're well equipped to enhance the performance and efficiency of your Spark applications. Keep experimenting, as there's always more. Now let's see how we can implement data aggregation in Spark using DataFrames. We begin by importing the necessary libraries and initializing a Spark session. Following that, we define a dataset containing sales transactions, represented as tuples with product names, quantities sold, and revenue generated. This dataset is transformed into a data frame with clearly defined column names, product, quantity, and revenue. Next, we will write the following code to aggregate revenue generated by each product. By utilizing the group by method, we group our data frame based on the product column. This allows us to compute the total revenue for each product by applying the AGG function with sum, effectively calculating the sum of the revenue column. The resulting data frame, named total revenue, now contains the total revenue generated by each product, which we can display using the show method. This process demonstrates a fundamental yet powerful feature of Spark data frames, enabling us to derive meaningful insights from our data through aggregation. Now let's explore how to compute a running total of revenue by product using Spark's window functions. This powerful feature allows us to perform calculations across a subset of rows related to the current row, enhancing our data analysis without collapsing it into a single summary row. First, we define a window specification that partitions the data frame by the product column and orders the rows by revenue. This partitioning is crucial as it lets us calculate the cumulative revenue for each product independently. Next, we use the withColumn method to introduce a new column called running total. Here, we apply the sum function over our defined window, effectively calculating the cumulative sum of revenue for each product as we iterate through the data frame. By executing this code, we enrich our dataset with insightful information on how revenue accumulates over time for each product. This provides us with valuable insights into sales trends, empowering us to make more informed business decisions. Finally, we display the resulting data frame equipped with the new running total column to visualize the cumulative revenue for each product. Next, we will write the following code to demonstrate how to remove duplicate records from a data frame. First, we define a dataset containing several product entries, some of which are duplicated. This sample data is structured as a list of tuples, which includes the product name, quantity, and revenue. We then create a data frame from this data, ensuring we have a structured format for our analysis. Now let's implement the crucial step of cleaning our data using the drop duplicates function. This powerful function examines our data frame and systematically removes any duplicate rows, retaining only unique records. It's particularly valuable in data processing because duplicates can distort analytical outcomes and lead to erroneous insights. After applying the drop duplicates function, we display the clean data frame using the show method. This method allows us to visually inspect the data frame and confirm that we've successfully eliminated duplicates, setting a solid foundation for further data analysis and transformation. Now let's see how we can implement a user-defined function, UDF, to categorize revenue into different levels, such as low, medium, or high. First, we begin by importing the necessary modules from PySpark, specifically the UD function and the string type, which will define the return type of our UDF. Next, we define a Python function named categorizeRevenue that captures our categorization logic. Inside this function, we use conditional statements to assign a category based on the revenue value. If it is less than 100, it returns low. If it's between 100 and 299, it returns medium. and for values 300 and above, it returns high. Once our function is defined, we register it as a UDF using the UD function, specifying that it returns a string type. Now, let's implement the UDF on our data frame using the withColumn method, which allows us to create a new column named Revenue Category. By passing in the existing revenue column, we can apply our categorization logic seamlessly. Afterward, we display the data frame with the new column to visualize our categorizations, enhancing our data analysis capabilities. Now let's see how we can implement a simple linear regression model using Spark's mlib. First, we define our sample data for the linear regression, consisting of pairs of features and labels, and specify the column names as features and label before creating a data frame from this data. This data frame is crucial, as it allows us to work seamlessly with Spark's machine learning library. Next, we utilize the vector assembler, which is a vital tool for transforming our input data into a format that mlib can understand. Specifically, it converts the features column into a feature vector. After executing this transformation, we initialize a linear regression object and fit it to our prepared data frame. This step trains the model by finding the best fit line for our data. Finally, we print the model's coefficients and intercept, which not only describe the relationship between the features and the predicted values, but also provide critical insights into the data dynamics. With this straightforward example, we can appreciate how easy it is to implement machine learning algorithms with Spark, enabling us to focus more on interpretation rather than the underlying complexity. Now let's see how we can implement graph processing in Spark using GraphX, which is particularly useful for analyzing relationships within data, such as social networks. First, we initiate a Spark context and a Spark session, which are essential for any Spark application, allowing us to interact with the cluster and manage resources effectively. Next, we define our graph structure by creating two parallelized collections, one for vertices and one for edges. The vertices represent individuals in our social network, identified by unique IDs and their corresponding names. Meanwhile, the edges define the relationships between these individuals, in this case, depicting a follow relationship where one person follows another. Once we establish the vertices and edges, we proceed to create a graph using the graph constructor. With our graph structure in place, we can leverage GraphX's powerful functionalities. Finally, to visualize our graph, we print the vertices and edges, which helps us understand the relationships and connections within the data. This basic example sets the stage for more complex graph analysis, such as computing page ranks or identifying connected components. Now let's see how we can implement real-time data processing using Spark with a streaming data frame sourced from a Kafka topic. First, we create a Spark session to set up the environment for our streaming application. It's crucial to provide the application name to help identify the job in the Spark UI. Next, we define a Kafka data source using the readStream method. We specify the format as Kafka and provide necessary options, such as the Kafka Bootstrap servers and the topic from which we want to subscribe to incoming messages. This configuration establishes the connection to the Kafka topic, allowing Spark to read live data streams effectively. After defining the data source, we process the incoming stream by transforming the key and value fields into string formats using the selectExpr method. This casting simplifies subsequent data manipulation and analyses. Finally, we initiate a streaming query that outputs the processed data to the console in append mode, meaning new data will be continuously displayed as it arrives. The query await termination method ensures that the streaming application will run until we decide to stop it, making it a powerful tool for real-time data insights. As we conclude this lesson on advanced data processing techniques, we've traversed a wide array of topics that truly showcase the power and flexibility of Spark. We explored aggregation, window functions, data cleaning, user-defined functions, machine learning, graph processing, and real-time data streaming. These advanced techniques will enable you to handle a multitude of data scenarios and derive actionable insights with ease. Always remember to experiment with these functionalities. They are designed to help you make the most out of your data processing tasks. Your adventure in mastering Spark is just beginning, and by continuing to dive into these advanced techniques, you'll become adept at extracting the most value from your data. Keep exploring, keep doing, and share your findings with others. Thank you for joining me in this journey. Now let's see how we can implement a Spark session in our application. The first step is to import the Spark session class from the PySpark SQL module, which serves as the entry point for all functionalities in Spark. In the next line, we create a Spark session using the builder method. Here we set the application name to MySpark application by using the appName method, which is important for tracking the application in a Spark UI, making it easier to monitor and manage. We can customize the Spark configuration options to suit our needs. For instance, the config method allows us to specify various Spark settings. In this example, we include a placeholder for a configuration option, demonstrating how you might alter Spark's behavior to optimize performance or functionality. Finally, we call the getOrCreate method, which either retrieves an existing Spark session if it's already available or creates a new one if not. This ensures that you maintain a single instance of your Spark session throughout your application, thus enhancing efficiency and resource management. Now let's see how we can implement a Spark application that effectively processes data from a CSV file. To begin, we load the data into a data frame using the Spark read CSV method. Here, we specify the path to our CSV file and set the header option to true, indicating that the first row contains the column names. The infer schema option allows Spark to automatically infer the data types of each column, which is crucial for accurate data processing. Once we have loaded the data, the next step is to preview the first few rows of the data frame with the show method. This helps us verify that the data has been loaded correctly and gives us a chance to assess its structure and contents. After examining the data, we can perform a transformation by selecting specific columns and applying a filter condition. In this case, we select column 1 and column 2 while filtering for records where column 3 exceeds 100. This transformation is key for narrowing down the dataset to what is specifically relevant for our analysis. Finally, we execute an action by counting the number of records that meet our filter criteria using the count method, and we print the result. This simple yet effective operation demonstrates how to manipulate and analyze data efficiently with Spark. Next, we will implement the command to submit our Spark application while managing its dependencies effectively. When deploying Spark applications, especially in cluster environments, it's essential to ensure that any external libraries needed for your program are accessible. To achieve this, we use the PyFiles flag, which allows us to include zipped files containing our external libraries during the submission process. For instance, in our command, dependencies zip is specified as a zipped file that contains all necessary Python packages required by our application. This step is crucial because it guarantees that all the components your Spark job depends on are readily available in the execution environment. By ensuring that these libraries are included, we prevent potential runtime errors and facilitate smoother execution of the application. Thus, the command not only launches the specified Spark application, but simultaneously ensures that it operates with all the necessary resources at its disposal. Properly managing these dependencies is a key practice in building robust Spark applications that can run effectively across different setups. Next, we will write the following code to create a Spark session optimized for performance. This session serves as the entry point for interacting with Spark functionalities. Here, we configure several properties that are crucial for effective resource management. Specifically, we set the number of executor cores to 4, which allows for greater parallel processing capabilities by distributing tasks across multiple cores simultaneously. This configuration can significantly enhance application performance, especially during heavy computations. Additionally, we allocate 8 GB of memory for each executor and 4 GB for the driver. Proper memory allocation ensures that we have enough resources to handle larger datasets without running into memory bottlenecks. This setup is essential when you are working with big data, as it maximizes the efficiency of data processing. It's important to tailor these parameters to what your cluster can handle based on available resources. To conclude, this optimized Spark session configuration is a crucial step in building robust Spark applications. Now let's see how we can save our transformed data frame in a more efficient format using Parquet. The first line of code indicates the initiation of the data frame write operation, specifically configured to overwrite any existing data using the mode overwrite option. This feature is particularly useful as it allows for easy updates to the dataset without the need for manual cleanup of previous files, thereby streamlining data management. Next, we specify the Parquet format for saving the data frame by invoking the Parquet function and providing a designated directory path where the file will be stored. This choice of format leverages Parquet's columnar storage capabilities, which not only improves speed during data retrieval, but also reduces storage space through efficient compression techniques. Once we've saved the data frame, we can easily read it back into Spark. In the following line, we utilize the read Parquet method to load the data from the specified Parquet file. This straightforward process showcases the seamless integration of Spark with Parquet, allowing users to access their data efficiently while maintaining a focus on performance optimization. Through this approach, we can take full advantage of Spark's capabilities in handling large datasets effectively. Now let's implement the following logging mechanism to enhance our Spark application. First, we import the logging module, which provides a flexible framework for emitting log messages from Python programs. We then set up basic configuration for logging by calling basic config with a specified log level of info. This means that all messages at this level and higher, like warning, error, etc., will be recorded. Next, we create a logger object specific to our Spark application using getLogger, naming it Spark Application for clarity. This logger will help us track events and any issues that arise during the execution of the application. As we begin our Spark application, we log an informational message stating that the application is starting. Now let's see how we can handle potential errors that may occur during execution. By wrapping our Spark logic in a try-except block, we can catch exceptions and log them as errors. In this case, if there is an issue reading a CSV file into a data frame, we output an error message along with the details of the exception. This structured logging not only facilitates debugging, but also contributes to the maintainability of the application by making it easier to trace the application's flow and diagnose issues quickly. To promote a balanced load among partitions and enhance performance in Spark applications, it's essential to utilize the repartition method effectively. Now let's see how we can implement this by adjusting our data frame to have 100 partitions. By partitioning the data more evenly, we mitigate the performance bottlenecks that can occur when dealing with skewed data distributions. These bottlenecks often arise during operations like joins, where unevenly distributed data can overload certain partitions while leaving others underutilized. By calling DataFrame repartition 100, we ensure that Spark redistributes the data across 100 partitions, which allows for better parallelism and resource utilization during subsequent operations. This practice is particularly beneficial when shuffling data between partitions, as it minimizes the risk of running into execution delays. A well-balanced partitioning scheme can lead to significant performance improvements, especially in data-intensive applications where large datasets are handled. So incorporating the repartition method into your data processing workflow is a crucial step toward efficient resource management and optimized application performance. Now let's see how we can implement unit testing for our Spark applications using Python's unitest framework. First, we create a test class that inherits from unitest test case, allowing us to structure our tests efficiently. In the setup class method, we initialize a Spark session which serves as the context for our tests. This method runs once for the entire class, setting up the required environment. Next, we define a test method named testTransformation, where we will validate our transformation logic. Here, we create a simple data frame containing names and values, and then apply a filter operation to extract records with values greater than 10. After applying the transformation, we employ an assertion to check that the resulting data frame indeed contains one row, indicating that our filter is functioning correctly. This approach ensures that our transformation logic behaves as expected. Finally, the teardown class method is implemented to stop the Spark session after all tests have been executed. This cleanup step is crucial for freeing up resources and maintaining a clean testing environment. Through this testing structure, we can systematically check for code correctness as we develop and modify our Spark applications. Now let's implement the following command to submit our Spark application to a Kubernetes cluster. This command is crucial for running your application in a distributed environment and allows you to take advantage of Kubernetes orchestration capabilities. We start by specifying the master URL for the Kubernetes API server, which is essential as it directs Spark to the location of your cluster. The deploy mode is set to cluster, meaning Spark will manage the application within the cluster without requiring a local Spark session. Additionally, we name our application myK8s app, allowing us to identify it easily within the cluster management interface. Next, we designate the main class of our application, which contains the executable code, followed by a configuration option that allows you to customize settings specific to your application. Finally, we indicate the path to the packaged application file, in this case, a jar file containing your Spark application. By using this command, you ensure that your application is deployed efficiently within the Kubernetes environment, leveraging its resource management features and scalability benefits, enabling your Spark applications to handle larger datasets and complex workflows seamlessly. Now let's see how we can implement data filtering in Spark using a data frame. In this snippet, we first read a CSV file containing user information into a data frame named users.df. The Spark read CSV method is employed, where we specify the path to the CSV file. We also opt for the header equals true parameter to treat the first row as the header containing column names and infer schema equals true to automatically determine the data types of the columns based on the CSV content. Next, we focus on filtering the data frame to extract users who are older than 25 and reside in New York. We achieve this by utilizing the filter function, which takes a condition where we combine two criteria, users DF age 25 and users DF city equals New York, connected by the logical AND operator. This single filtering operation not only simplifies the logic, but also allows Spark to optimize how the data is processed, leading to a more efficient execution plan. By consolidating our data processing in this manner, we maximize Spark's performance by minimizing the complexity and resource usage involved in executing multiple transformations. Now let's see how we can implement effective data partitioning in Spark using the coalesce and repartition methods. When working with large data frames, it is essential to manage the number of partitions effectively to optimize resource utilization and task parallelism. In our first example, we use the coalesce method to reduce the number of partitions in a data frame called users.df to 10. This is particularly useful when the data frame is too heavily partitioned, minimizing overhead and helping to balance the load on executors without incurring the costs of a data shuffle. This operation consolidates the data, leading to more efficient execution. Next, we want to perform an expensive join operation on the same data frame. To thoroughly distribute the data before the join, we can use the repartition method to increase the number of partitions to 20. By reshuffling the data across more partitions, we enhance parallelism, thereby potentially speeding up the join operation and optimizing resource distribution. Both techniques are vital tools for managing performance in Spark applications, emphasizing the importance of appropriate partitioning strategies based on the dataset size and the computational tasks at hand. Now let's see how we can work with Parquet format in our Spark application. The first line of code demonstrates how to write a data frame, in this case, users.df, to a Parquet file. By using the write method coupled with mode overwrite, we ensure that if the file already exists in the specified path, it will be replaced. This is particularly useful for iterative development when you expect to modify data frequently. After writing our data frame to Parquet format, we then proceed to read it back into a new data frame, new users.df. This operation is achieved by calling SparkReadParquet, which reads the data stored in the specified Parquet file. Utilizing Parquet is advantageous because it supports efficient data processing techniques. For instance, when stored in a columnar format, Spark can intelligently load only the required columns, enhancing performance, especially with large datasets. This showcases not only how to handle data in Parquet format, but also highlights the performance optimizations that come with using efficient data formats in Spark applications. Now let's see how we can implement a broadcast join in our Spark application to optimize performance during data processing. In this example, we start by reading two datasets, one large and one small, from CSV files. It is crucial to choose the correct way to read data to ensure Spark handles the datasets efficiently. Next, we use the broadcast function from the PySpark SQL functions module on the smaller data frame before performing the join. By broadcasting the smaller dataset, we ensure that it gets replicated across all worker nodes. This not only minimizes the data movement across the network, but also reduces the computational overhead associated with shuffling. The join is executed on a specified key column, allowing Spark to efficiently combine records from both data frames based on matching values in this column. By following this practice, we significantly enhance the performance of joins when dealing with large datasets. This technique exemplifies one of the key strategies for optimizing Spark applications by effectively managing shuffles and improving resource utilization. Now let's see how we can implement caching to optimize the performance of our Spark application. Caching is a powerful technique that allows us to store intermediate results in memory so they can be reused in subsequent operations without needing to recompute them. In the provided code, we call the cache method on the users.df data frame which instructs Spark to keep the contents of this data frame in memory for quicker access. Once the data frame is cached, the first action that we perform on users' DF, such as counting the number of users, triggers the caching process. This means that although it may take some extra time initially to cache the data frame, subsequent actions are expedited since they can leverage this persisted data. This is especially beneficial in scenarios that involve iterative computations or multiple actions that reference the same data frame. However, one important point to keep in mind is that caching consumes memory resources. Therefore, it's essential to monitor memory usage and only cache data frames that will be reused frequently to ensure efficient resource management. Now let's see how we can implement Spark configurations to optimize our Spark application effectively. The code begins by creating a Spark session, which is crucial for every Spark application, as it serves as the entry point for working with data frames and APIs. We use the builder method to set up this session and assign it a name, in this case, Optimized Spark Application. In this configuration, we specify several critical parameters to enhance performance. Setting Spark Executor cores to 4 allocates 4 CPU cores for each executor, which can improve parallel processing. The line Spark Executor memory is set to 8 GB, thereby allocating 8 GB of memory to every executor, providing the necessary resources for handling larger datasets efficiently. We also configure Spark driver memory to 4 GB, which ensures the driver has adequate memory for its operations, especially when processing intermediate results. Furthermore, we adjust the number of shuffle partitions with Spark SQL shuffle partitions, set to 100, which optimizes data distribution during shuffles. By fine-tuning these settings, you can tailor the Spark application to better meet the workload demands and available cluster resources, leading to significant performance improvements. Now let's take a look at how we can optimize garbage collection in our Spark application by configuring the Java Virtual Machine (JVM) options. Proper configuration of the JVM can significantly reduce the pauses caused by garbage collection, enabling smoother execution of Spark jobs. In our implementation, we create a Spark session, which is essential for any Spark application. We specifically set the application name to Garbage Collection Optimized Spark Application for clear identification in the Spark UI. To optimize garbage collection, we add configurations for both the executor and driver by using the config method. Here, we set Spark Executor Extra Java options and Spark Driver Extra Java options to use the G1 garbage collector, which is known for its ability to minimize pause times during execution. By adopting this configuration, we help the JVM manage memory more efficiently, leading to improved performance and reduced delays in long-running Spark applications. Understanding and setting these JVM options is crucial for any Spark developer aiming to enhance performance and resource management capabilities within their applications. Finally, leveraging the power of the Spark UI is an invaluable resource for optimization. The Spark UI provides insight into the execution plans, stages, and tasks of your applications. Monitoring these metrics can pinpoint issues such as long-running tasks, skewed partitions, and memory usage. You can access the Spark UI typically at http://drivernode4040, where you can refine your applications based on real-time performance indicators. For better performance, regularly review your application's DAG, directed acyclic graph, to identify bottlenecks and inefficiencies. By analyzing task execution times, data skew, and resource allocation, you can iteratively optimize your Spark applications to achieve peak performance. In conclusion, optimizing Spark performance requires a multifaceted approach that touches on various aspects of the execution process. By minimizing transformations and actions, optimizing data partitioning, selecting efficient data formats, managing shuffles, caching results, configuring Spark settings, tuning JVM options, and using the Spark UI for monitoring, you can establish powerful and efficient Spark applications. Remember that each application may have unique needs, so continuous evaluation and adjustments are key to maintaining optimal performance. Armed with these strategies, you are now equipped to elevate your Spark applications, driving efficiency and scalability to new heights. Thank you for joining me in this exploration of Spark performance strategies. In this segment, we'll be diving into real-world case studies that showcase the application of Apache Spark across various industries. These case studies illustrate not only the versatility of Spark, but also its ability to tackle large-scale data processing challenges effectively. Today, you will see how different companies have harnessed this powerful tool set to solve unique problems and drive innovation. So far, we learned about enhancing Spark application efficiency through strategic optimization practices, including minimizing transformations and actions, effective data partitioning, and choosing optimal data formats like Parquet. We discussed the importance of caching intermediate results, managing Spark configurations, techniques to reduce shuffles, and the impact of garbage collection on execution time. Finally, we emphasized the use of the Spark UI for monitoring performance and identifying areas for further optimization. Now, we will cover specific case studies demonstrating Spark's application in real-world scenarios. Now let's see how we can implement a real-time stream processing application using Spark streaming. First, we initialize the Spark context and define a streaming context with a batch interval of 10 seconds, which allows us to process the streaming data in manageable chunks. Next, we create a Spark session to work with data frames, enabling us to easily manipulate and analyze the structured data we will receive. The following step is to establish a dstream that connects to a source of incoming data, in this case, a socket that listens on localhost at port 9999. This setup allows us to receive data continuously from the configured source. Now, let's define a function called processData, which will handle the incoming lines of text. Inside this function, we split each line into components corresponding to product information, specifically the product ID, timestamp, and amount, and transform this data into a data frame. Finally, we use the for_each_rdd method to apply our processData function to each batch of data received. This enables us to act on the data as it streams in, allowing the retail company to gain insights and make decisions in real time. By starting the computation with SSC start, we set the application into motion, waiting for new data until we decide to stop the process. Now let's see how we can implement data processing using Apache Spark SQL to handle call records for our telecommunications case study. First, we initialize a Spark session, which is essential for creating data frames and using Spark's features. The Spark session serves as an entry point to interact with Spark's capabilities. Next, we load the CSV file containing call records into a data frame. Specifying the header equals true option allows Spark to infer the column names from the first row of the CSV file, creating a structured dataset that we can work with. Once the data frame is ready, we create a temporary view to execute SQL queries directly against this data frame. This step is crucial, as it allows us to use familiar SQL syntax to interact with our data. For example, we construct a query to count the number of calls for each customer by grouping them based on their customer IDs. This aggregation provides valuable insight into customer behavior, which is essential for tailoring services and reducing churn. Finally, we display the results of the query, enabling the telecom provider to make informed decisions quickly based on real-time insights. Now let's see how we can implement a machine learning pipeline for fraud detection using PySpark. First, we create a Spark session, which acts as the entry point to any Spark functionality. The session is initiated with a specific application name, fraud detection, allowing us to monitor and manage our application easily. Next, we load our training data from a CSV file containing transaction data, ensuring we include the header for clarity. Once the data is loaded, we need to perform feature engineering to prepare it for model training. We select relevant columns, amount, location, and transaction time to be used as features for our predictive model. Using the vector assembler, we combine these features into a single vector column called features, which is essential for the logistic regression algorithm we'll utilize. Now we will train our model by instantiating a logistic regression object and fitting it to the transformed dataset. The model here is trained to recognize patterns associated with fraudulent transactions. Finally, we use this trained model to make predictions on the transformed data, allowing us to see the predicted labels alongside the transaction amounts. This process illustrates how we can leverage Spark's machine learning capabilities to effectively detect fraud in real-time transactions. Now let's see how we can implement a healthcare analytics solution using PySpark. First, we establish a Spark session, which is essential for interacting with Spark's capabilities and processing data. By using Spark Session Builder, we initiate a session named Healthcare Analytics, allowing us to organize our operations effectively. Next, we load the patient data from a JSON file into a data frame. This step is crucial since it enables us to work with structured data, which can be easily analyzed. Once the data is loaded, we need to transform and analyze it to extract valuable insights. we group the patient data by medical condition, calculating the average treatment costs and counting the number of patients for each condition using the AG function. This aggregated view is beneficial for decision-making as it helps optimize treatment strategies based on cost-effectiveness and patient volume. Finally, we employ the show method to display the resulting healthcare report, providing a clear overview of the aggregated metrics. This reporting allows healthcare providers to tailor their services and allocate resources more efficiently, ultimately improving patient care outcomes. Now let's take a look at how we can implement user engagement analytics using Apache Spark. First, we create a Spark session, which is the entry point for working with Spark's functionalities. It allows us to configure and manage our Spark application efficiently. In this case, we've named the application User Engagement Analytics. Next, we load the application logs from a Parquet file, which is an efficient columnar storage file format that helps us manage large datasets effectively while retaining schema information. After loading the data, we utilize Spark's powerful DataFrame API to perform aggregation. We group the logs by feature name and count the occurrences of userid within each feature, allowing us to gauge user engagement for every feature available in the application. This computational operation is crucial because it transforms raw log data into actionable insights regarding which features keep users engaged. Finally, we display the results of this aggregation, providing us with valuable metrics to inform decisions on feature enhancements. Through this process, we can directly see Spark's capability to handle large datasets and derive meaningful analytics efficiently. Today, we are diving into the advanced features and capabilities of Apache Spark that enhance performance and usability, making it an unparalleled choice for big data processing. This lesson will explore the intricate tools and techniques Spark offers, paving the way for you to leverage its full potential in your data-driven projects. So far, we learned about the real-world applications of Apache Spark through various industry case studies, including retail, telecommunications, finance, healthcare, and technology. We explored how companies utilized Spark for real-time analytics, predictive modeling, and data integration to enhance operational efficiency and improve customer experiences. Additionally, we discussed the importance of leveraging Spark's capabilities, such as machine learning and structured data querying, to drive innovation and data-driven decision-making. Each example demonstrated Spark's versatility in solving unique data challenges across different sectors. Now, we will cover advanced features like Spark SQL, the Catalyst Optimizer, DataFrames, and various performance tuning techniques, ensuring that you become a proficient Spark user. Now let's see how we can create a Spark data frame from a JSON source and execute SQL queries on it. First, we start by initializing a Spark session, which is essential as it allows us to configure and manage Spark's execution context. Once we have the session, we proceed to load data into a data frame from a JSON file containing people's information. Data frames are versatile structures that enable us to process data efficiently with named columns. Next, we create a temporary view named people. This view acts as a bridge, allowing us to write and execute SQL queries directly on our data frame, which is one of the powerful features of Spark SQL. Following this, we formulate a SQL query that selects names and ages from the people view, filtering out anyone younger than 21. This simple yet effective query showcases how seamlessly we can mix SQL with Spark's data processing capabilities. Finally, we call the show method to display the results, demonstrating how easy it is for data analysts and engineers to harness Spark SQL for insightful data analytics. Now let's see how we can leverage the Catalyst Optimizer to enhance our data frame operations in Spark. In this example, we start by filtering the data frame to include only individuals over the age of 21 using a straightforward condition. This operation is pivotal because it allows us to reduce the dataset to only the relevant subset, optimizing the processing time and resources needed for subsequent operations. Once we have our filtered data frame, we proceed to select only the necessary columns, specifically the name and age attributes. This step minimizes data movement across the Spark cluster and maximizes cache utilization, which are key benefits provided by the Catalyst Optimizer. By executing these actions in a single sequence, Catalyst intelligently optimizes the underlying execution plan, ensuring that our computations are efficient and fast. Finally, we can visualize the results by invoking the show method, which displays the filtered data frame. This concise example successfully demonstrates how Catalyst can streamline complex operations while maximizing performance, reinforcing the sophisticated capabilities of Spark SQL in handling big data challenges effectively. Now let's see how we can implement a group by operation using data frames to analyze sales data. In this example, we begin by loading our sales data from a CSV file into a data frame, specifying that the first row contains headers and allowing Spark to infer the data types of each column. This flexibility simplifies the data loading process, as we do not need to manually define schemas. Once we have the sales data in a data frame, we can perform a group by operation. Here, we group the data by the product column, which enables us to aggregate our sales figures for each unique product. The aggregation function calculates the sum of the amount column, giving us the total sales for every product. This is particularly powerful, as it allows for quick insights into sales performance without the need for complex queries. Finally, we display the results using the show method, which outputs the grouped sales summary directly to the console. This straightforward approach highlights how data frames in Spark streamline data processing and analysis, empowering users to gain insights efficiently while leveraging Spark's distributed computing capabilities. Now let's implement a simple linear regression model using Spark's mlib library, which leverages the power of distributed computing for machine learning tasks. First, we create a vector assembler, which is essential for preparing our data. This tool consolidates multiple feature columns into a single column labeled features, facilitating the input for our model. Next, we transform our data frame, data, into a format suitable for training the model by applying the vector assembler. Once the data is transformed, we split it randomly into training and test sets, assigning 70% of the data for training and 30% for testing. This split is crucial for evaluating our model's performance on unseen data. With our training data ready, we proceed to create a linear regression model, specifying the features and labels. After fitting the model on the training data, we can then use it to make predictions on the test dataset. Finally, we display the original features, actual labels, and the predictions made by the model. This process highlights the streamlined workflow of building a machine learning pipeline in Spark, showcasing how accessible and efficient it can be to work with large datasets. Now let's see how we can implement memory tuning in our Spark application. In this example, we begin by creating a Spark session using Spark Session Builder, which is the entry point for using Spark functionalities. We specify a unique application name, Memory Tuning Example, which helps identify this instance of our Spark job in clustered environments. To address the memory management aspect, we use the config method to set the configuration option, Spark Executor Memory, to 4G. This is a critical step because it allocates 4 GB of memory to each executor, which are the distributed processes responsible for executing tasks in Spark. By increasing the executor memory, we enhance Spark's ability to handle larger data volumes and complex computations, thereby reducing the risk of memory overflow errors that can occur during execution. Finally, we call getOrCreate to either retrieve the existing Spark session or create a new one if none exists. This setup ensures that our Spark application is well configured for optimal performance and ready to process large datasets efficiently. Now let's see how we can control the data partitioning to enhance performance when processing large datasets in Spark. To achieve this, we can specify the number of partitions during the data reading process. In the provided code, we read a large CSV file, ensuring that the data is loaded efficiently while maximizing parallel processing capabilities. By using the repartition method and setting it to 10 partitions, we allow Spark to distribute the data across multiple nodes effectively. This partitioning strategy is crucial because it strikes a balance. Too few partitions may lead to resource underutilization, while too many can create unnecessary overhead due to increased task scheduling. In practice, monitoring the data distribution across these partitions can provide valuable insights into how well our data is balanced. This is where the Spark UI becomes beneficial, as it allows us to visualize and adjust the number of partitions based on our observations. Such optimizations not only improve performance but also ensure that Spark can execute tasks more efficiently, leading to quicker results in our data processing workflows. Now let's implement caching for our data frame. Caching is a powerful feature that improves performance by storing the data frame in memory after the initial computation. This way, any subsequent actions performed on the data frame can quickly access the cached data rather than recalculating it, saving time and resources. First, we will invoke the cache method on our data frame. This marks it for caching and triggers Spark to compute its contents when the next action is invoked. In this example, we will subsequently execute a count action, which forces the calculation and populates the cache with the data frame's data. Once the count operation completes, the data frame is cached in memory, ensuring that the next action performed, like showing the data frame's contents using the show method, can utilize the cached data. This demonstrates how caching enables efficient reuse of data frames in your computations. However, it's important to manage memory, as caching consumes resources, so you should unpersist data frames when they are no longer needed to optimize performance further. Now let's see how we can implement data reading from cloud storage using Spark. In this code, we are pulling data from an Amazon S3 bucket directly into a Spark data frame, which is a fundamental step in processing data with Spark. The Spark read CSV function is utilized to read data from a specified path, in this case, S3A / your bucket name / data CSV. The header equals true parameter indicates that the first row of the CSV file contains column headers, making the data frame easier to work with by automatically naming the columns. Additionally, the infer schema equals true option instructs Spark to identify and assign the appropriate data types to each column based on the content of the CSV file, enhancing the usability of the data frame for further analysis. This versatile capability of Spark to connect with cloud storage solutions like S3 allows data engineers and analysts to leverage big data architectures efficiently, ensuring seamless data processing irrespective of the storage location. So to summarize what we have covered today, we dove deep into the advanced features of Apache Spark, including Spark SQL, the Catalyst Optimizer, data frames, and machine learning integration through mlib. We discussed crucial performance tuning techniques such as managing memory and data partitioning, along with caching for efficiency. Lastly, we explored Spark's ability to integrate with various data sources to create a unified data processing workflow. With these advanced capabilities up your sleeve, you're now better equipped to harness Spark for complex data challenges and drive impactful insights from your data. Spark stands as an outstanding tool for any data engineer or analyst looking to excel in the big data landscape, providing the power and flexibility to turn your data into action. Thank you for joining this tutorial, and I hope you apply these advanced features in your upcoming projects. To achieve optimal performance in Spark applications, understanding and implementing best practices for performance tuning is essential. In this session, we'll dive into strategies to enhance your Spark applications, ensuring they run efficiently and effectively. So far, we've explored the advanced features of Apache Spark, including Spark SQL, the Catalyst Optimizer, and data frames, along with their applications in big data processing. We also covered performance tuning techniques such as memory management and data partitioning to enhance efficiency. Additionally, we discussed the integration of machine learning with Spark through the mlib library and the importance of caching for performance benefits. Now we will discuss best practices for Spark performance tuning that will elevate your applications to the next level. Now let's take a look at how we can configure our Spark application to optimize memory usage. In the provided code, we initiate a Spark session, which is the entry point to any Spark functionality, and we specify essential configurations related to memory allocation. Here, we are setting the Spark executor memory configuration to allocate 4 GB of memory for each executor. This is critical for ensuring that each processing unit has sufficient memory to handle its workload, particularly when dealing with large datasets. Additionally, we specify Spark driver memory to 2 GB, which allocates memory to the driver program that coordinates the cluster. These memory settings are vital as they help reduce the risk of memory-related errors and performance bottlenecks. By allocating appropriate memory, we can minimize garbage collection interruptions, thus enhancing the execution speed and throughput of our data processing tasks. This step demonstrates the importance of tuning memory settings in achieving efficient and robust Spark applications that can handle varying workloads effectively. Now let's implement the following steps to cache a data frame for optimal performance in our Spark application. First, we begin by loading data from a CSV file into a data frame using Spark's read method. This method is particularly powerful as it can automatically infer the schema of the data, making it easier to work with without requiring extra configuration. Once we have our data frame loaded, the next important step is to cache this data frame in memory using the cache method. Caching plays a crucial role in performance tuning, as it allows frequently accessed data to reside in memory, reducing latency in subsequent operations. By calling data cache, we instruct Spark to retain this data frame in memory after its initial computation. Finally, to ensure that our cache is materialized, we need to trigger an action. In this case, we use the count method, which will execute the computation and load the data into memory. This means that for all subsequent actions performed on this data frame, Spark will utilize the cached version, eliminating the need for recomputation and thereby significantly enhancing performance during data processing tasks. Next, we will write the following code to read a large dataset efficiently and manage its partitions. By using the Spark read CSV method, we specify the path to our CSV file, ensuring that it includes header information and infers the data types automatically. However, a critical part of enhancing performance lies in managing how this data is partitioned in Spark. To optimize parallel processing and reduce the chances of encountering bottlenecks, we utilize the repartition function right after loading the data. In our case, we specify 10 partitions for the data frame. This approach enables the workload to be evenly distributed across the available executors, allowing Spark to process multiple partitions in parallel. By having an appropriate number of partitions, we take full advantage of Spark's distributed computing capabilities, effectively reducing overall processing time. Managing partitions in this way is a vital step in ensuring your Spark application runs efficiently, particularly when dealing with large datasets. Now let's take a look at how to optimize join operations in Spark by broadcasting a smaller data frame. In this example, we begin with two data frames, where one, df1, is large and contains a significant amount of data, while the other, df, is comparatively small. To minimize shuffle overhead and improve performance, we first broadcast the smaller data frame, df. The broadcast function is utilized here to send a copy of df2 to each executor, thus reducing the amount of data that needs to be shuffled across the network during the join operation. Next, we perform the join using the join method on df1, along with the broadcasted version of df. This approach ensures that the join operation occurs efficiently, as both data frames share the same key. The key benefit of this technique is that it significantly cuts down on the network transfer load, allowing Spark to process data more swiftly and effectively. This method is particularly useful when dealing with large datasets where optimal performance is crucial, making it a valuable addition to your Spark performance tuning toolkit. Next, we will explore how to compute the average value of a specific column within a data frame by grouping the data based on another column, which in this case is category. This approach utilizes Spark's efficient data frame API, allowing us to leverage its optimization capabilities. Now let's write the following code to achieve this. First, we import the necessary functions from the PySpark SQL module, which includes various built-in functions that aid in data manipulation and aggregation. We then perform a group by operation on the category column, which organizes the data into distinct groups based on the unique values found in that column. Next, we apply the ag function, where we calculate the average of the value column for each category using f(avg), renaming the resulting column to average value for clarity. Finally, by calling averages_show, we visualize the results to see the average values computed for each category. This method not only illustrates the power of data frames, but also demonstrates the efficiency gained by using built-in functions rather than performing the aggregation through RDD transformations. Now let's see how we can implement filter pushdown while reading data from a Parquet file in Spark. In the example, we load a Parquet file by using the SparkReadParquet method, which is a built-in functionality of Spark that allows us to efficiently read Parquet formats. To enhance performance and minimize unnecessary data transfer, we apply a filter directly by chaining the filter method with a condition that specifies we only want records where the age is greater than 21. This approach ensures that Spark processes only relevant data, leading to reduced I/O operations and better overall resource utilization. By filtering the data at the source level, we avoid pulling in all records, which would lead to increased processing time and network traffic. Finally, the show method is used to display the filtered results, providing an immediate view of the data that meets our criteria. This technique is a practical demonstration of filter pushdown, underscoring its critical role in optimizing Spark jobs for improved performance. Next, let's highlight the significance of monitoring and tuning resources via the Spark UI. The Spark Web UI provides valuable insights into job execution, allowing you to diagnose bottlenecks and identify areas for performance improvements. By checking the stages and task execution times, you can discern whether your resources are utilized efficiently or if adjustments are necessary. When a job runs, navigate to the Spark UI at http://your-sparkmaster4040. You'll see overview metrics such as total tasks, stages, and executors. By analyzing these stats, you can pinpoint long-running stages or tasks and take action, such as rewriting job logic or modifying configurations. Furthermore, you can monitor the executor memory and storage metrics to ensure you're optimizing the allocated resources correctly. For example, if you see a heap memory nearing the limit, you may consider increasing the executor memory or optimizing your data processing to stay within resource limits. Next, we will write the following code to properly configure resource allocation for our Spark job. By utilizing the Spark Session Builder, we initiate a new Spark session, which is essential to begin any Spark application. The appName method allows us to assign a descriptive name to our application, making it easier to track in the Spark UI. To manage resources effectively, we set two critical configurations: Spark Executor Memory and Spark Executor Cores. Here, we allocate 4 GB of memory to each executor, which ensures that they have adequate resources for processing tasks without running into memory-related issues. Additionally, by setting Spark Executor Cores to 4, we enable each executor to run 4 concurrent tasks. This configuration helps maximize parallelism, allowing our job to utilize available CPU resources efficiently. Choosing the right balance between memory and cores is essential for optimal performance and prevents misallocations that can hinder processing speed. Monitoring the Spark UI will help us assess the impact of these configurations, guiding further adjustments for improved resource management. Now let's implement the following configuration options to optimize garbage collection in our Spark application. By adding the JVM options shown, we instruct Spark to leverage the G1 garbage collector, which is designed for applications running with large heap sizes. This garbage collector is advantageous because it minimizes the time spent in garbage collection pauses, crucial for maintaining the application's responsiveness, especially when processing significant datasets. Command specifies Spark Executor extra Java options, allowing us to pass extra parameters directly to the Java virtual machine that Spark executes on. The Roman 20 plus use G1 GC option activates the G1 garbage collector, enhancing performance by efficiently managing memory and reducing pauses. Additionally, we set XX max GC pause mil is equals 20, which suggests to the garbage collector to strive to keep pause times under 20 milliseconds. This proactive tuning ensures smoother application performance as it reduces lag during memory reclamation processes. By integrating these options into your Spark job launch, you can significantly enhance its performance and overall efficiency when dealing with large-scale data processing tasks. In conclusion, mastering performance tuning in Apache Spark is an essential skill for anyone working with big data applications. By leveraging best practices such as proper memory management, effective caching strategies, optimal data partitioning, and efficient resource allocation, you can significantly enhance your Spark application's performance. Always remember the substantial impact of using built-in functions and minimizing data shuffles while being vigilant about garbage collection settings. By monitoring jobs through the Spark UI and ensuring the correct configurations are in place, you're well equipped to tackle any big data challenge with confidence. With these strategies at your disposal, you will empower your Spark applications to unlock their full potential, leading to faster and more efficient data processing. Thank you for joining this session on Spark performance tuning, and I hope you take these insights into your future projects for thrilling data success. As we wrap up our exploration of Apache Spark, it's essential to reflect on its evolution and consider what lies ahead for this powerful tool. This session will encapsulate the core aspects of Spark we've covered so far and discuss the exciting future developments on the horizon. So far, we learned about the importance of performance tuning in Spark applications, focusing on memory management and caching to enhance efficiency. We discussed how to optimize data partitioning and minimize shuffles to align workloads effectively. Additionally, we covered the significance of using appropriate DataFrame operations and filter pushdown for improved performance. Lastly, we emphasized the need to monitor resources through the Spark UI and adjust configurations for optimal execution. Now we will explore the future directions for Spark and its potential impact on big data processing. Now let's implement a simple linear regression model using Spark's mlib to predict housing prices based on house size. First, we begin by initializing a Spark session, which serves as the entry point for any Spark functionality, allowing us to interact with various data processing features. Next, we create a data frame that simulates sample housing data, consisting of 3 columns: an identifier, the size of the houses, and their corresponding prices. In preparing the data for our linear regression model, we utilize the vector assembler, which combines the features into a single vector column, a necessary step because Spark's machine learning models require input data in this format. Once the data is assembled, we can create our linear regression model by specifying which column represents the features and which one serves as the label to predict, in this case, the price of the houses. After fitting the model to our training data, we gain insights by displaying the model's coefficients and intercept, essential metrics that inform us how the model behaves and predicts pricing based on the size of the houses. This straightforward yet powerful approach illustrates how Spark facilitates machine learning tasks effectively on large datasets. Now let's implement a res-tful approach for submitting Spark jobs using the requests library in Python. First, we define the API endpoint that will handle our Spark job submission. In this case, it's essential to know the address of the Spark cluster you are working with, which is specified in the URL. Next, we prepare a JSON payload that contains the necessary details for the job you'll be submitting. This includes specifying the application's name, the path to the code file stored in your HDFS, the main class to be executed, and any Spark arguments such as memory allocation and the number of executors required for the job. These parameters are crucial, as they dictate how the Spark application will run in terms of resource allocation. Once the payload is structured, we make a POST request to the defined URL, sending our JSON payload. It's important to handle the response from the server to verify whether the job was submitted successfully or if there was an error. By checking the status code returned, we can provide feedback on the job submission process. This model not only simplifies the interaction with Spark, but also allows for effective job management in dynamic data environments. Another exciting prospect for Spark is the potential increased focus on serverless architectures. As organizations move their infrastructure to the cloud, the demand for on-demand resources grows sharply. Serverless computing allows users to run applications without managing the underlying servers, streamlining operations and focusing more on code rather than infrastructure. Imagine automatically deploying Spark applications that respond to data events in real time. For example, an e-commerce platform might process customer transactions and analyze trends almost instantaneously to tailor user experiences based on the data. As serverless technologies advance, we can easily envision Apache Spark functioning as a serverless offering, where users can run jobs in response to events without worrying about server management or provisioning. Now let's see how we can configure and submit Spark jobs to a Kubernetes cluster using the Spark submit command. This command is crucial for running your Spark applications in a cloud-native environment. In this scenario, we start by specifying the master URL for the Kubernetes API server, allowing Spark to connect to the Kubernetes cluster. The deploy mode cluster option tells Spark to launch the driver program within the cluster rather than on the client machine, optimizing resource utilization and management. Next, we define the application name, SparkPy, which helps identify the job running in the cluster. Additionally, we indicate the primary class, org Apache Spark examples, SparkPy, that Spark will execute, and we provide the path to the application jar file, local //opt/spark/examples/jar/spark examples, jar. Finally, we pass an argument, 100, which is used by the SparkPy example to compute the value of pi using a number of samples. This snippet serves as a foundational step for deploying Spark in Kubernetes, emphasizing the importance of mastering this orchestration tool for efficient data processing in the cloud. In the same spirit of innovations, the concept of enhancing Spark's capabilities around data privacy and security emerges as a pivotal area to examine. With growing concerns about data breaches and privacy regulations like GDPR and CCPA, the need for frameworks to maintain high security is greater than ever. Spark's future could see the integration of robust encryption techniques for data at rest and in transit, ensuring sensitive information remains protected throughout its life cycle. Furthermore, as organizations embark on big data projects, the ability to control access and permissions within shared Spark environments will become increasingly critical. Future developments may include advanced user management and role-based access control mechanisms, enabling administrators to dictate who can access specific datasets or execute certain Spark jobs. Lastly, learning and education surrounding Apache Spark will continue to evolve. With the rapid pace of technological advancements, keeping skills current is essential for data professionals. Future initiatives may encompass comprehensive educational resources, interactive platforms, and hands-on workshops that provide ongoing learning opportunities for individuals looking to enhance their Spark expertise. Imagine participating in a community-driven learning environment where users can collaborate on Spark projects, share insights, and develop skills together. Online platforms could evolve to facilitate real-time coding sessions, mentoring opportunities, and knowledge sharing, fostering a dynamic ecosystem fully dedicated to advancing big data capabilities. In conclusion, Apache Spark stands at a fascinating crossroads, equipped with a powerful foundation and numerous possibilities ahead. As we've discussed, the future of Spark lies in its ability to adapt and integrate with emerging technologies, enhance interoperability, and prioritize security and learning. The continued growth of machine learning, serverless architectures, and cloud-native deployments will shape Spark's development in the years to come. As we move forward, embracing these changes and trends will empower data professionals to harness Spark effectively, driving innovation and transforming how we process and derive insights from big data. The exciting journey ahead promises a seamless blend of power, efficiency, and creativity that will redefine the data landscape, and it's a journey we all want to be part of. Thank you for joining me today, and I'm thrilled to see how you'll carry these insights into your practice. Keep exploring and pushing the boundaries of what Spark can achieve. To run Apache Spark with Python, also known as PySpark, you need to understand the essential requirements and configurations to set up your environment properly. Today, we will delve into the critical aspects of the Spark Python requirements and how to set them up effectively. This knowledge will lay the foundation for efficiently using Spark in Python for big data processing and analysis. So far, we learned about Apache Spark's evolution and its future potential in big data processing. We covered key topics such as performance tuning, data optimization, and machine learning with Spark's mlib. Additionally, we discussed promising developments like serverless architectures, Kubernetes integration, and enhanced security measures. As we continue, we'll explore the specific requirements for setting up PySpark and how to implement them practically. Now let's see how we can verify that both Java and Python are installed on your machine, which is essential before proceeding with Spark setup. First, we will check the Java installation by running a command that provides the version number. This feedback allows us to ensure that Java is installed correctly, as Apache Spark relies on Java to function. If you see an appropriate version number, you're good to go. Otherwise, you'll need to install or update Java. Next, we will verify your Python installation using a similar approach. This command will also return the version number of Python currently installed on your machine. It's crucial here to confirm that you have Python 3x, as it is recommended for using PySpark effectively. If you see the version number, it's an indication that Python is ready for use. If not, you'll need to install Python. Having both Java and Python correctly set up is the first step in creating a functional Spark environment with PySpark. Next, we will write the following commands to download and set up Apache Spark on your system. The first command uses wget, a command line utility for downloading files, to fetch the Spark binary package from the official Apache website. Make sure to use a URL that corresponds to the specific version of Spark you intend to install, as shown in the example. Once the download is complete, the second command, tar_xvf, is used to extract the contents of the downloaded tgz file. This extraction will create a new directory containing the Spark files needed for its operation. After extraction, it's essential to properly position the Spark files in a system-wide accessible directory. This is accomplished using the sudo mv command, which moves the extracted Spark folder to opt_spark, a common location for optional software installations on Unix-like systems. By placing Spark in this directory, you can easily configure your environment variables in the next steps, ensuring that your system recognizes Spark's location and can execute it seamlessly. These steps are crucial in establishing a functioning Spark environment for data processing and analytics. Now let's implement the necessary environment variable configurations to properly set up Apache Spark with Python. First, we define the Spark home variable, which points to the directory where Spark is installed. This is essential because it establishes the location for the Spark binaries and libraries. Next, we modify the path variable to include the Spark binaries folder, allowing you to run Spark commands directly from the terminal without specifying the full path each time. Additionally, we set PySpark to specify the Python version that PySpark should use, which is particularly important if you have multiple Python versions installed. In this case, we're pointing it to Python 3, but you should adjust it based on your Python setup. Finally, we set PySpark driver Python to Jupyter to ensure that the PySpark application is launched within a Jupyter notebook environment, making it easier to work interactively with your data. After adding this configuration to your profile, don't forget to source the file to apply the changes in the current terminal session. This ensures that your configurations are recognized and utilized for a smooth running experience with PySpark. Now let's check if PySpark is installed correctly by running it in the terminal. Simply typing PySpark will launch the PySpark shell, providing you with a welcoming Spark message if everything has been set up properly. This step is crucial for confirming that your Spark installation is functional. Next, we will enhance our Python environment by installing some essential packages that don't come with PySpark, but are incredibly useful for data analysis and visualization. The packages Pandas, NumPy, and Matplotlib are widely used in the data science community. They allow for managing data structures, performing numerical computations, and generating visual representations of data. To install these libraries, we will utilize pip, Python's package installer. Running the command pip install pandas numpy matplotlib will download and install these packages into your Python environment, setting you up for more advanced data manipulation and analysis. These libraries will serve as invaluable tools as you begin to analyze and visualize your data using PySpark, complementing its functionalities and enhancing your overall productivity in data processing tasks. Now let's see how we can configure our Spark session with specific memory settings for both the driver and executors. To create a Spark session, we start by importing the Spark session class from the PySpark SQL module. We then use the Spark session builder method to initiate the creation of our Spark application, where we set the application name using the appName method. Next, we specify crucial configuration parameters using the config method. In this case, we are defining the memory allocation for the Spark driver and executors, setting both to 2 GB. This allocation is crucial as it directly impacts the performance and resource management of your Spark application. By configuring the driver and executor memory, you ensure that your application has enough resources to handle data processing tasks efficiently. Finally, we call the getOrCreate method to either retrieve an existing Spark session or create a new one with the specified configurations. This step is essential as it establishes the environment from which you can interact with Spark. With this setup, you are now well equipped to optimize resource usage within your Spark environment as you begin to process and analyze big data. Now let's see how we can configure the number of cores allocated to the Spark executor process. In a Spark application, managing resources effectively is crucial, especially when working on a multi-core machine or in a cluster. By specifying the number of cores, you can optimize performance and enable your application to handle larger datasets more efficiently. In our code, we start by creating a Spark session using the Spark session builder method. This initiates our Spark application with a given name using the appName method. To set the number of cores for the executor, we call the config method and specify Spark executor cores with a value of 4. This means that the executor process will be assigned 4 cores, allowing it to perform parallel processing more effectively. This configuration is particularly beneficial when dealing with complex data operations, as it can significantly enhance the performance of your Spark jobs. By managing the number of cores wisely, you will ensure that your application runs smoothly and can scale according to the workload. Hence, understanding and configuring these settings is essential for optimizing your Spark applications. Now let's implement a simple PySpark operation by creating a data frame. Data frames are a fundamental data structure in PySpark, allowing for efficient data manipulation and analysis. We start by defining a dataset in the form of a list of tuples, where each tuple represents a record. In this case, we have 3 records, with each record containing a name and a value. This format makes it easy to represent structured data. Next, we also define the corresponding column names as a list, which makes our data frame more informative and easier to work with. Once we have our data and column names, we can utilize Spark's createDataFrame method to generate the data frame. By passing our data and column names to this method, Spark transforms the list into a structured format that allows us to perform various manipulations and analytics. Finally, we invoke the show method on our data frame. This command displays the data frame in a tabular format, providing us with a quick overview of our data and confirming that the data frame has been created successfully. This simple operation lays the groundwork for more complex data processing and analysis tasks using PySpark. In conclusion, setting up PySpark requires you to ensure that you have Java and Python properly installed, followed by downloading and configuring Spark. The environmental variables play a crucial role in ensuring that your system can locate Spark in Python. With proper configuration of memory and cores, alongside using an IDE like Jupyter Notebooks, you can provide a conducive environment for big data processing with PySpark. As you proceed with your learning journey in big data analytics with Apache Spark, remember that these setup requirements will significantly impact your development and execution experience. Now that you have a solid foundation, you're ready to dive deeper into the world of Spark with Python. Next, we will cover more advanced topics, including Spark SQL and DataFrame operations, which will further enhance your skills. Keep practicing and happy. To run Spark applications using Cloudera, we need to set up the environment correctly to leverage Cloudera's capabilities effectively. This lesson will focus on configuring your Spark setup within Cloudera to ensure smooth operation. We will also cover running Spark applications, utilizing Cloudera Management Console, and examining helpful best practices. So far, we learned about the prerequisites for running PySpark, including the necessity of having Python and Java installed. We discussed methods for installing Apache Spark from binaries and highlighted the importance of configuring environment variables for seamless operation. Additionally, we covered configuration parameters for optimizing memory and cores and the advantages of using an IDE like Jupyter Notebooks for an interactive coding experience. As we move forward, we will explore more advanced topics such as Spark SQL and DataFrame operations. Let's begin by discussing the specific setup requirements for Cloudera. When you install Cloudera's distribution of Apache Spark, it comes bundled with other essential components like Apache Hadoop, Hive, and Yarn. This integration allows for streamlined data processing and resource management. Therefore, before running Spark applications, it's crucial to ensure these components are installed and configured properly within the Cloudera ecosystem. To get started, you'll need to access the Cloudera Manager interface, where you can manage your clusters. Once you have Cloudera installed and running, open the Cloudera Management Console. This web-based interface will be your main control center. Navigate to the Clusters tab, where you will find the cluster you set up. Click on the cluster to access details and components. Here is where you would typically check whether Spark is listed among the services running in your cluster. If Spark is not installed yet, you can add it using the Cloudera Manager. Click on the Add Service option, select Spark, and follow the prompts to install it. During installation, you can configure important parameters such as the version of Spark you wish to use and whether you want to include optional services like Spark SQL. The Cloudera Manager offers guided setup, making it user-friendly even for those new to big data processing. Once installed, you should verify that your Spark service is up and running. You can do this by visiting the Spark service page in Cloudera Manager, which provides metrics and logs to ensure everything is functioning correctly. Here, you can also access Spark's job history server, which is vital for tracking your Spark application's performance and any issues that may arise. Now let's implement the code that establishes a basic Spark application using PySpark. We begin by importing the Spark Session module, which is essential for creating a Spark session. Next, we invoke the builder to initiate our Spark session, providing it a name with the app name parameter. This is particularly useful for monitoring and tracking your application's performance in the Cloudera environment. Once the Spark session is created, we define some sample data in the form of a list of tuples representing names and corresponding values. This dataset will serve as a foundation for our data frame. Following that, we specify the column names as a separate list and use the createDataFrame method to convert our data into a data frame. This allows us to leverage the power of Spark's distributed computing capabilities. Next, we display the data frame content using the show method, confirming that our data has been loaded successfully. Additionally, we implement a simple transformation where we add a new column called newValue, which computes double the original value. This is a foundational operation demonstrating how to manipulate data within Spark, showcasing the framework's strength in handling versatile data transformations efficiently. Now let's see how we can configure our Spark application to optimize resource utilization when running on Cloudera's platform. In this setup, we start by creating a Spark session, which is essential for interacting with the Spark engine. We specify the application name as Cloudera Spark Example, helping us identify the job later on. Next, we proceed to configure several important parameters to manage the resources effectively. For instance, we set the executor memory to 2 GB, ensuring that each executor has enough memory to handle tasks efficiently. We also specify that the application should use 4 executor instances, allowing for parallel processing of tasks, which is crucial for performance in a multi-application environment. Additionally, we assign 512 MB of memory to the application master, which is responsible for coordinating the execution of the Spark job. By adjusting these settings, we enhance the performance of our Spark applications and ensure that we make the best use of the available resources in the Cloudera ecosystem. It is vital to tailor these configurations according to both the capability of your cluster and the specific requirements of your Spark jobs. After configuring and running your Spark job, you might want to monitor the progress and performance. Cloudera offers robust monitoring tools to visualize application metrics. Within the Cloudera Management Console, you can navigate to the Spark Application section to see an overview of your application's performance statistics such as execution time, job success rate, and memory usage. Additionally, Spark provides the Spark UI, which is an invaluable tool for debugging your applications. You can access the Spark UI from the Cloudera Management Console or directly through the web interface dedicated to Spark. The UI presents detailed information about jobs, stages, and tasks, along with resource usage. Furthermore, it allows you to identify bottlenecks and optimize your Spark job's performance. Let's take a look at some useful features within the Spark UI. You'll find several tabs, including Jobs, Stages, and Storage. In the Jobs tab, you can review all the jobs executed by the application, including their statuses and execution times. The Stages tab breaks down jobs into individual stages, allowing you to inspect their performance. The Storage tab gives you insights into the data cached in memory, helpful for optimizing access patterns. Now let's see how we can use data frames in Spark to filter our dataset efficiently. In the code provided, we begin by applying a filter to the data frame, specifically selecting rows where the value column is greater than 1. This operation is achieved through the filter method, which allows us to express a condition, here, df value 1. By using data frames instead of RDDs, Spark takes advantage of its Catalyst optimizer, which can perform various optimizations that enhance query performance. The filtering operation is not only straightforward but also efficient, as it maintains data locality, minimizing the costly data shuffles that can occur with other transformation methods. This approach ensures that our data is processed quickly and effectively. Once we apply the filter, we use the show method to display the resulting data frame. This allows us to verify that only the intended rows are included in our output. This pattern of operation is fundamental when working with larger datasets, as it emphasizes both performance and clarity in your data processing workflow. Lastly, always be sure to clean up your resources once your Spark job has completed. Cloudera Manager provides a straightforward way to stop or restart Spark services when they are no longer in use. Always keep track of running applications and terminate any that you no longer need. This helps prevent resource leaks and keeps your cluster running smoothly. You can stop applications directly from the Cloudera Management Console or programmatically within your code. In conclusion, running Spark applications with Cloudera involves careful setup and configuration, taking advantage of Cloudera's management tools and integration with Yarn for resource allocation. By following best practices, leveraging the Spark UI, and using data frames, you can optimize your data processing and analysis workflows. As you continue exploring Spark, we will delve into more advanced topics, including Spark SQL and data frame operations to further enhance your skills. Until next time, keep coding and exploring the power of big data with Spark. Now let's see how we can create a Spark session, which is the foundation for any Spark application using PySpark. We start by importing the Spark Session class from the PySpark SQL module, which is essential for working with Spark functionality. Next, we use the builder method to initiate a builder object that allows us to configure our session. One of the key configurations we implement is setting an application name using the appName method. This custom name helps us identify our application in the Spark monitoring interfaces, making it easier to track its performance and resource utilization. After specifying the application name, we finalize the creation of the Spark session by invoking the geTorCreate method. This method checks if a Spark session already exists. If so, it reuses that session instead of creating a new one. This practice is beneficial for resource management, ensuring efficient use of system resources. Once completed, we have established our Spark session, which serves as the entry point for executing Spark-based applications and enables us to harness the full potential of PySpark for big data processing. Now let's see how we can load data into a data frame from a CSV file. In this example, we utilize the read method from our Spark session, which provides a user-friendly interface for loading data. The CSV function is called with the path to the CSV file as its argument. It's essential to set the header parameter to true, indicating that the first row of the CSV file contains the names of the columns. This saves us from having to manually define column headers later on. Additionally, by enabling infer schema, we empower Spark to automatically deduce the data types of each column based on the content. This feature simplifies our workflow by eliminating the need to specify data types explicitly, thereby streamlining the data loading process. Now that we've successfully loaded the data into a data frame, we can examine its contents to ensure it's been imported correctly. By calling the show method, we can view the first 20 rows of the data frame. This command provides immediate insight into our dataset, allowing us to verify data integrity and understand its structure at a glance. This step is crucial as it enables us to confirm that our data has been loaded as expected before proceeding with further analysis. Now let's see how we can filter our data frame to focus on users from a specific country. In this code, we leverage the filter function, which allows us to create a new data frame, filtered df, containing only the rows where the country column is equal to USA. This operation is particularly useful for narrowing down our dataset to only the relevant entries, enabling more targeted analysis. After creating filtered df, we use the show method to display these filtered results, providing a clear view of which users meet our condition. Next, we will write the following code to extract specific columns from our data frame, a crucial step when dealing with wide datasets. By utilizing the select method, we can create another data frame, selected df, which contains only the name, age, and country columns. This operation streamlines our focus, allowing us to manage the data more efficiently and prepare it for further analysis. Just like before, we'll employ the show method to visualize the contents of selected df, ensuring we have successfully narrowed our dataset to the columns of interest. Now let's implement the following aggregation to find the average age of users in our dataset. We begin by using the group by method on the data frame, specifying the country column as our grouping criterion. This action clusters the data based on unique country values, allowing us to apply aggregate functions to each group separately. The ag function is then utilized in this case to calculate the average age through the avg operation on the age column. The result is stored in a new data frame called average age, which will contain each country along with its corresponding average age. To visualize our results, we call the show method, which displays the average age for each country in a clear tabular format. Next, we will write a similar operation to count the number of users per country. Again, we use the group by method, focusing on the country column. This time, however, we apply the count function directly, which tallies the total number of entries associated with each country. As with the previous operation, the count of users is saved in a new data frame called user counts, and the show method is used to display the results. With these simple yet powerful aggregation functions, we can extract significant insights about our dataset, enabling data-driven decision-making. Now let's implement a transformation that allows us to enhance our dataset by adding a new column for senior citizens. In this example, we utilize the withColumn method to create a column named isSenior. We will leverage the when function to evaluate whether the age of each user is 65 or older. This function will return true for seniors and false for others. By doing this, we enrich our data frame with meaningful insights that can be invaluable for analyses revolving around age demographics without altering the original data structure. Next, we will also look at how we can modify the existing column for salary. By applying the withColumn method again, we will increase the salary of all employees by 10%. This demonstrates the power of PySpark's transformations, allowing us to perform complex updates efficiently across entire columns while maintaining the integrity of our original dataset. Each of these operations showcases how we can manipulate and enhance our data, facilitating more informed decision-making and analysis in our projects. Now let's explore how to perform an inner join between two data frames. In this operation, we utilize the join method, which is invoked on the first data frame, df1, with the second data frame, df, as the argument. This method requires us to specify the column to join on through the on parameter, which in our case is userid. The how parameter indicates the type of join we're implementing. Here, we've chosen an inner join. The outcome of this operation is a new data frame that contains only those rows where the userid values match in both data frames. This merging of data is particularly useful for enriching datasets with complementary information, enhancing the overall analysis quality. Next, we will look at a common task in data processing, eliminating duplicate entries from a data frame. We can achieve this using the drop duplicates method, which efficiently removes any duplicate rows based on the specified column, which is userid in our example. By calling this method on our data frame, we ensure that only unique instances of userid are retained, resulting in a refined dataset. This step is crucial in maintaining data integrity and ensuring that subsequent analyses are based on clean and reliable data. Now let's implement the following configuration for our Spark environment. The Spark Session Builder initiates the creation of a new Spark session, which is essential for interacting with any Spark functionality. By calling the appName method, we assign a meaningful name to our application, which is helpful for monitoring purposes. Next, we configure memory settings to optimize our application's performance. Specifically, we specify that each executor should have access to 4 GB of memory, while the driver can utilize 2 GB. These settings are crucial since they directly impact how efficiently our application runs, especially as the data volume increases. Now let's see how we can manage the distribution of our data efficiently. To enhance parallelism, we can utilize the repartition method, which allows us to increase the number of partitions in our data frame. In this case, we are repartitioning our data frame into 8 partitions, which helps in optimizing the workload distribution across the cluster. On the other hand, if we find our partitions are too numerous after processing, we can efficiently reduce their count using the coalesce method. This step is vital when aiming to decrease the processing overhead and optimize resource usage after transformations, ensuring our job runs smoothly. Now let's see how we can visualize the data we have processed using PySpark. To begin, we first import the necessary libraries: Pandas, which is a powerful data manipulation library, and Matplotlib, a widely used library for creating static, animated, and interactive visualizations in Python. Next, we convert the PySpark data frame into a Pandas data frame using the toPandas method. This conversion is essential because while PySpark is excellent for handling large datasets in a distributed manner, it does not provide built-in visualization tools. Converting the data frame to Pandas allows us to leverage various visualization capabilities available in Python. Once we have our data in a Pandas data frame, we can create a histogram to visualize the distribution of ages in our dataset. The hist function is called on the age column of the Pandas data frame, specifying the number of bins for the histogram. This function will group the ages into specified intervals, helping us to see how the values are distributed. Finally, we add titles and labels to our plot using title, xlabel, and ilabel functions, and then we call show to display the histogram. This process not only helps convey insights, but also makes our findings more accessible. Now let's see how we can create a resilient distributed dataset (RDD) from a log file, which is crucial for distributed data processing with Spark. By using the Spark context text file method, we specify the path to our log file. This command initializes the RDD called log_RDD, which contains all the lines of the log file, effectively breaking down our data into manageable pieces systematically distributed across the cluster. The beauty of this command lies in its simplicity and efficiency. Spark automatically manages data distribution and provides the ability to perform various transformations and actions on the RDD. This enables you to focus on deriving valuable insights instead of being bogged down by the complexities of data logistics. By creating this RDD from the log file, we can utilize Spark's powerful processing capabilities to analyze the data efficiently, allowing us to tackle large datasets without the need for intricate data management tasks. This sets the foundation for subsequent operations such as filtering and aggregating data, bringing us closer to discovering meaningful patterns in our logs. Now let's see how we can implement a filter transformation on our RDD to specifically target and count the instances of a 404 not found status in our web traffic log. We start by using the filter function, which allows us to create a new RDD, not found RDD, that consists solely of the lines from log RDD where the string 404 is present. This operation is lazy, meaning it only sets up the transformation without executing it until an action is called. Next, we will invoke the action count on our newly created not found RDD. This action triggers Spark to execute the transformations we've set up and actually process the data. The result will be an integer representing the total number of log entries that contain the 404 status code. We then use a print statement to display this count, providing a clear output that informs us of how many 404 not found errors occurred in our logs. This implementation exemplifies how Spark efficiently manages large datasets, allowing us to focus on analytics rather than the intricacies of the code syntax itself. Now let's see how we can implement the transformation of our RDD into a data frame to utilize its optimized functionalities. First, we start by creating a list of row objects from the RDD. Specifically, we map each line of the RDD, extracting the relevant fields such as the status, code, and URL using a Lambda function. This approach not only organizes the data into a structured format, but also makes it easier to work with. Next, using createDataFrame, we convert this list of rows into a data frame named log.df. By encapsulating the structured data within a data frame, we gain the advantage of Spark's performance optimization features, which allow for more efficient querying and manipulation of the data. Finally, to verify that our data frame has been created successfully, we can invoke the show method. This method displays the first few rows of the data frame, providing a quick glance at the organized data and confirming that the transformation from RDD to data frame was executed correctly. Overall, this step is crucial in preparing our data for further analysis and generating insights with ease. Next, we will look at how to summarize our log data by counting occurrences of each status code using the data frame we're working with. By applying the group_by method followed by the count function, we can efficiently aggregate the data based on the status column. This operation groups the data frame entries that share the same status code and then computes the count for each group, providing a clear picture of how many times each status appears in our logs. Once we execute this, we can then call show on the resulting data frame, which conveniently displays the aggregated results. This concise syntax facilitates rapid data exploration, enabling you to quickly glean insights into the frequency of various status codes, which is essential for monitoring web traffic and diagnosing potential issues. Thus, the power of Spark is fully realized as we can process and analyze large datasets like this within seconds, helping decision-makers access vital information promptly and accurately. Now let's see how we can optimize our data processing by using broadcast variables in Spark. To start, we create a dictionary named userLookup that contains mappings of user IDs to usernames, which serves as a small lookup table. This data is particularly useful when we have a large dataset that needs to reference these usernames frequently. By broadcasting this dictionary using Spark's broadcast method, we can efficiently share this data across all the nodes in the cluster without incurring the overhead of transferring it multiple times during task execution. Next, we implement a transformation on our previously created RDD, log_RDD, to enrich our log entries with the corresponding usernames. We do this by mapping through each line of the log and using the broadcasted variable to look up the username. For every log entry, the user's ID is extracted from the line, and we use the get method on the broadcasted variable to retrieve the username. If an ID is not found, it defaults to unknown. This approach not only enhances our log information, but also minimizes data transfer, ultimately leading to faster processing and improved performance in our Spark application. Next, we will write the following code to optimize the performance of our data frame by repartitioning it based on the status field. This operation is crucial as it rearranges the data frame's data to ensure that records with similar status values are placed together in the same partition. By doing this, we can significantly speed up query times, especially if we frequently analyze or filter the data frame using the status field. When Spark processes this repartitioning, it redistributes the data across the available partitions according to the specified key, which in this case is status. This means that Spark will create a more balanced distribution of data, reducing the time it takes to retrieve information from the data frame when querying by status. However, it's important to remember that while repartitioning can enhance performance by increasing parallelism, excessive partitioning can lead to overhead and diminish returns. Thus, it's essential to consider your dataset's characteristics and workload to choose an optimal partitioning strategy. Now let's see how we can effectively cache our data frame to enhance performance. Caching is a crucial optimization technique in Spark that allows us to store data in memory for faster subsequent access. When working with large datasets that require multiple operations, like filtering or aggregating, invoking the cache method on our data frame is highly beneficial. This command ensures that when the data frame, in this case log_df, is accessed for the first time, Spark loads it into memory. As a result, all future operations on this data frame will reference this cached data, eliminating the need for Spark to recompute the entire dataset. Such efficiency proves especially valuable during iterative tasks or when performing several queries on the same dataset. By caching, we significantly reduce processing time, enabling quicker insights and allowing us to focus on data analysis rather than on performance bottlenecks. In practice, this step helps smooth our workflow in a Spark application, making it a necessary consideration when optimizing your data processing strategies. Now let's see how we can implement error handling while processing log data in Spark. The process log function is designed to extract specific details, namely the status code and URL, from each line of the log. To ensure robustness, the code employs a try-except block, which allows it to gracefully handle potential errors. If the line does not contain enough parts to retrieve the desired information, an index error would normally occur. However, the use of the try-except structure prevents the function from crashing. Instead, it returns none, indicating that the line was invalid. Following this, we utilize Spark's map transformation to apply this function across every entry in the log RDD, which contains our log data. This allows us to create a new RDD, where each valid log line is transformed into a tuple of its status code and URL. To filter out any invalid entries resulting from lines that caused exceptions, we then apply a filter operation, which checks for none values. This method ensures that our Spark application continues to run smoothly, even when some log lines might not meet the expected format. Now let's take a look at how we can visualize the frequency of HTTP status codes from our log data. The code begins by importing the necessary libraries, pandas and matplotlib, which are essential for data manipulation and visualization in Python. We then convert our Spark data frame, log.df, into a pandas data frame using the toPandas method. This transition is crucial, as it allows us to leverage the powerful functions provided by pandas for easy data analysis and plotting. Next, we count the occurrences of each status code in the data frame by accessing the status column and using the valueCounts method. This method returns a series containing counts of unique values, which we can then plot. The visualization is created as a bar chart by calling the plot function with the kind parameter set to bar. This instantly gives us a clear visual representation of how frequently each status code appears in the logs. Finally, we enhance the chart's readability by adding a title and a label for the y-axis, and we display the plot using PLT show. This visual approach effectively translates raw data into understandable insights, making it accessible for various stakeholders. Let's examine the function update Spark config, which plays a vital role in customizing your Spark environment. This function begins by changing the directory to the location of the Spark configuration files. This is an essential step as it ensures that the following commands are directed at the correct files. Subsequently, we copy the template configuration file sparkenv sh template to sparkenv sh using sudo. This is a crucial action as it initializes the actual configuration file that Spark will use during runtime, helping to avoid potential execution failures caused by an improperly set up environment. Next, we define the Java home directory by adding the path to the sparkenv sh file. This specification enables Spark to find the Java runtime environment it needs for execution. Additionally, we determine the number of worker cores assigned for Spark jobs, setting it to 12, which helps optimize how Spark manages workloads across processors. In the final step, the function updates the slaves file with the IP addresses or hostnames of the machines within the Spark cluster. This process ensures that the Spark master can efficiently manage and distribute tasks among the available worker nodes. With these configurations completed, we are poised to enhance the performance and resource management of our Spark applications. Now let's implement the following Spark configuration settings to enhance our application's performance. We can begin by specifying resource allocation for our executors and driver, which directly affects how efficiently our Spark jobs run. For instance, we set Spark executor memory to 2G, indicating that each executor will have 2 GB of memory at its disposal. This helps prevent memory overflow errors during heavy data processing tasks. Next, we establish Spark driver memory as 4G to ensure that the driver has adequate memory to handle the orchestration of our Spark jobs. The additional configuration for Spark default parallelism, set to 100, dictates how the workload is divided among the executors. By allowing up to 100 partitions, we can achieve higher parallelism, effectively accelerating job completion. These configurations are applied when initializing the Spark session, allowing our application to dynamically adapt based on the resources available and the demands of our computations. This flexibility is particularly beneficial for applications that may need adjustments based on different cluster environments or workloads. Understanding and utilizing these configurations is crucial for optimizing performance and resource management in Spark. Now let's look at how we can set up a Spark session with specific configurations tailored for our application's needs. In this code snippet, we create a Spark session using the Spark Session Builder method, which is the entry point for working with Spark applications. The appNameMyApp method assigns a name to the application, which is useful for monitoring and managing jobs in the Spark UI. Next, we implement the configuration option SparkYarn Executor Memory Overhead, specifying it to be 512M. This parameter is important when using Yarn as the cluster resource manager because it allocates additional memory beyond what is allocated to the executors themselves. This overhead memory can be critical for handling large jobs, ensuring that Spark has sufficient buffer space to prevent out-of-memory errors during execution. By setting this configuration, we optimize the Spark application for better resource management, ensuring smoother performance under load. Finally, the call to get_create checks for an existing Spark session and returns it if found, otherwise it creates a new one. This method provides a convenient way to ensure we're always working with the correct Spark context, helping manage application state effectively across stages of processing. Now let's see how we can implement a key configuration to enhance the performance of our Spark applications by enabling speculative execution. The line of code we use is designed to set the Spark speculation configuration to true. This feature allows Spark to monitor the execution time of tasks, and if a particular task is detected to be significantly slower than its peers, Spark can schedule a duplicate instance of that task on a different executor. This approach is particularly useful in scenarios involving stragglers, tasks that take longer to complete and could potentially hinder the overall job progress. By enabling speculation, you ensure that no single slow task will hold up the completion of your entire job, thereby maintaining efficiency and timely execution. Furthermore, this configuration is easy to apply programmatically via the Spark configuration interface, allowing you to integrate it seamlessly into your application workflow. Utilizing this feature provides an added layer of fault tolerance, optimizing performance under varying workload conditions. Now let's take a look at how we can adjust Spark's configuration settings to optimize performance, particularly during shuffle operations. The line of code you see here sets the Spark SQL shuffle partitions to 200. This specific adjustment is important because shuffle operations can often become bottlenecks in distributed computations, especially when handling large datasets. By specifying the number of shuffle partitions, you effectively control how data is divided during operations like joins or aggregations. Choosing the right number of partitions is crucial. Too few partitions can lead to excessive resource bottlenecks, while too many can result in unnecessary overhead. In practice, you should consider the size of your data and the complexity of your transformations when determining this value. Setting it to 200 allows Spark to manage the shuffling of data efficiently, resulting in improved performance during heavy data transformations. Overall, understanding and appropriately configuring shuffle partitions is key to tailoring the execution environment to meet specific workload requirements, enhancing both the speed and efficiency of your Spark applications. Wrapping up this session, we've covered the essentials of Spark configuration management, focusing on how to effectively update and manage Spark settings to optimize performance. Through practical code examples, we've seen how to set up environment variables, manage worker nodes, and fine-tune job parameters across different settings. Going forward, ensure to monitor the specific needs of your applications and the nuances of your execution environment. This diligence will pay off in the form of reliable and efficient data processing with Apache Spark. Thank you for joining in today's discussion, and I look forward to our next topic where we will delve deeper into Spark optimizations and best practices. Now let's see how we can implement a Spark session using PySpark. We start by importing the Spark session class from the PySpark SQL module, which provides the necessary functionality to create our Spark session. By invoking Spark Session Builder, we begin the process of constructing a new session. We chain the appName method to specify a name for our application. This is particularly useful for tracking and monitoring, especially when running multiple applications simultaneously. Next, we use get_create to either retrieve an existing Spark session or create a new one if none exists. This approach is key in interactive environments as it prevents redundant session creation, which can lead to inefficiencies. This streamlined session management not only enhances resource usage but also ensures a smoother user experience. By following these steps, we set up our Spark environment, laying the groundwork for further data processing tasks and functionalities. Now let's explore how to set up the Spark session with enhanced configurations for better performance. We begin by specifying the master URL using the master method, which in this case is set to local asterisk. This tells Spark to utilize all available threads on the machine, making it ideal for local development and testing. Next, we can enrich our configuration by defining memory allocations for the driver and the executors. This is achieved through the config method, where we set Spark driver memory to 4G to allocate 4 GB of RAM for the driver and Spark executor memory to 2G for each executor. Proper memory allocation is essential, especially when working with large datasets, as it can significantly affect performance and prevent out-of-memory errors. With these configurations in place, we call get_create to either retrieve an existing Spark session or create a new one, ensuring that our application is ready to leverage Spark's powerful capabilities efficiently. This thoughtful setup paves the way for optimal performance throughout your application. Now let's take a look at how to retrieve and review the current configurations of our Spark session. The code iterates through all the configuration key-value pairs using the getAll method of the Spark context configuration. By executing this snippet, you effectively print each setting to the console, which is essential for validating that your Spark session is configured as expected. This process acts like a diagnostic check, ensuring that all personalized settings are correctly applied, much like double-checking the settings of your coffee machine before brewing. Next, we will implement a simple example of creating a data frame and utilizing SQL queries on it. The code starts by defining a sample dataset containing names and IDs, which we subsequently convert into a data frame named df. By creating a temporary view called people, we enable Spark SQL capabilities, allowing for a seamless execution of SQL queries on our data frame. Finally, we perform a SQL query to retrieve records where the ID is greater than 1. This functionality exemplifies the versatility of Spark, making it easier to interact with data in a familiar SQL-like manner, thereby enhancing your data processing capabilities. Now let's take a look at how we can enhance our Spark session with specific configurations that optimize performance for our data processing tasks. The first part of the code initializes a Spark session, where we set the application name to my Spark application. Importantly, we adjust the configuration for Spark SQL Shuffle partitions, reducing it from the default of 200 to 50. This change is particularly beneficial for smaller datasets, as it minimizes unnecessary shuffling during operations like joins and aggregations, leading to improved performance. Next, we move on to loading data into a data frame using the read CSV method. By specifying the path to our CSV file and including parameters such as header equals true to indicate that our data has a header row and infer schema equals true to automatically determine the data types, we ensure that our data is correctly interpreted for analysis. After loading the data, we call the cache method on the data frame. This action stores the data frame in memory, making it faster to access in future operations. By caching, we enhance the efficiency of our Spark job, especially when the data frame is reused multiple times. This approach consolidates resource usage and optimizes overall job execution. Now let's take a look at how to properly terminate a Spark session upon completing your work. The command Spark Stop is crucial for resource management within the Spark environment. This simple method instructs Spark to release all the resources it has allocated during the session, which includes memory and connections to compute nodes. By utilizing this command, you ensure that these resources are returned to either the Spark cluster or your local system, thereby preventing any unnecessary load or potential resource leaks. Neglecting this step can lead to performance issues, similar to wasting water by leaving a tap running. It's a best practice to always stop the Spark session when you're done, particularly in development environments where multiple sessions may be tested. Thus, by adopting this habit, you help maintain the efficiency of your working environment while safeguarding against unexpected challenges that can arise from resource mismanagement. With this understanding, we have covered the complete life cycle of a Spark session, encompassing both its creation and eventual termination. In this lesson, we'll explore the Spark environmental settings, a crucial aspect for configuring and running Apache Spark effectively. So far, we've learned about creating and initializing a Spark session, customizing configurations for performance optimization, managing memory allocations, and executing SQL queries on data frames. We also discussed the importance of stopping the session to conserve resources. Now we'll delve into the environmental settings that you need to consider when setting up your Spark environment, touching on Java configurations, board configurations, and Spark-specific environmental variables. Now let's see how we can implement the setting for the Java Home environment variable in our Spark configuration. This is a crucial step as it points Spark to the location of your Java installation, ensuring that it can access the necessary Java binaries when starting up. The command we will use involves echoing a specific string into the sparkenv sh file, which holds various environment configurations for Spark. The command constructs a new line that exports Java Home with the value of the Java destination, which should be replaced with the actual path to your Java installation. By employing the operator, we are appending this line to the end of the sparkenv sh file rather than overwriting its existing contents, ensuring that any prior configurations remain intact. This means that every time Spark launches, it will reference the Java Home environment variable you've just set, allowing it to locate Java seamlessly. Properly configuring Java Home is vital since any issues with Java not being found can typically be traced back to incorrect or missing settings in this file. Now let's implement the following command to configure the local IP address for Spark. The line of code appends a new export statement to the sparkenv sh file, which is a crucial configuration file for setting environment variables that Spark relies on during its execution. By using echo with the append operator, we ensure that our designated setting is preserved every time Spark starts. This particular command sets the Spark local IP variable, which specifies the IP address that Spark will use for communication within the cluster. Configuring this variable correctly is essential, especially in distributed environments, where precise networking settings can greatly enhance data transfer efficiency and connectivity between nodes. It's important to replace your local IP address with the actual IP address of the machine running Spark. Properly setting this variable can mitigate potential networking issues and ensure that your Spark applications can reliably communicate within the cluster, leading to improved performance and reduced chances of encountering connectivity errors. Now let's see how we can specify the master node for our Spark cluster. Setting the Spark master host variable is essential for directing your worker nodes to the correct master node where tasks and data are managed. In a local development environment, you might typically set this variable to localhost, ensuring that the worker nodes on your machine can connect to the master instance directly. However, when running on a distributed cluster, you'll need to replace your master node address with the actual address of your Spark master node. This change is crucial because it allows all worker nodes across the cluster to find and link up with the correct master node, which is responsible for scheduling tasks and coordinating the distributed processing. To implement this, you would add a line to your sparkenv sh configuration file using the specified command. By appending this line, you ensure that every time Spark is launched, it knows exactly where to find its master node, at which point worker nodes can successfully connect to retrieve instructions for processing data. This setup is pivotal for preventing connectivity issues and ensuring a smooth operation of your Spark applications. Now let's implement the following command to configure logging in our Spark environment. By setting the sparklog_dir environment variable, we can specify a dedicated directory for Spark logs, which is crucial for debugging and monitoring the application's performance. In this case, we are appending a line to the sparkenv sh file, which is the configuration file that holds environment settings for Spark. This command will ensure that all logging information generated by Spark will be directed to the specified log directory, making it easier to follow the application's behavior and troubleshoot any potential issues. It enhances our ability to maintain a clean and organized logging structure, crucial for analyzing Spark's activities. By replacing /path/ to /your/log/dir with the actual path where you want to store the logs, you provide a clear location that can be accessed anytime for inspection. A well-managed log directory will assist us immensely in identifying errors and performance bottlenecks, allowing us to optimize our Spark applications effectively. Remember, logging is not only about capturing errors, it's also about gaining insights into our application's performance and behavior during execution. Now let's implement a crucial environment variable that enhances the performance of your Apache Spark applications. To do this, we will set the Spark throttle scheduler environment variable in our sparkenv.sh file. This variable is essential for managing task execution, allowing for a fine-grained control over how requests are processed within your Spark cluster. By enabling the throttle scheduler, we ensure that Spark can manage request loads without overwhelming the cluster. This is especially beneficial in environments where multiple applications might be competing for the same resources, as it helps maintain a smoother workflow and reduces the potential for bottlenecks. You can think of it as a traffic control system. Just like a traffic light that coordinates vehicle flow, this setting optimizes resource allocation to ramp up operational efficiency. To activate this feature, we append a command to our configuration file, sparkenv.sh, which ensures that every time Spark starts, it knows to use this throttling mechanism. This proactive step leads to better overall cluster performance and smoother execution of tasks, making your Spark applications more robust and efficient. Now let's see how we can implement the maximum message size configuration specifically for Spark's remote procedure call (RPC) mechanism. By adjusting this parameter, we can ensure that Spark handles larger datasets effectively without failing due to oversized messages. The command appends a new line to the sparkenv.sh file, setting the environmental variable Spark RPC message max size to 512 megabytes. This adjustment is crucial for distributed applications, as it prevents data transfer failures that may occur if the configured message size is exceeded. When Spark tries to communicate between its various nodes, if the messages being sent are larger than the specified limit, it can lead to incomplete data transfers and unexpected outcomes. Therefore, setting an appropriate message size can drastically improve the stability of your Spark applications, particularly when working with voluminous datasets. Once this is configured, every time Spark is initiated, it will be able to accommodate larger messages, enhancing communication efficiency across your cluster. Now that we've set up various environmental variables, it's also a good practice to validate these configurations. Whether you're configuring a new cluster or working on a local environment, being able to check that all configurations are correct is crucial for a seamless experience. You can gain insight into your Spark setup by examining the Spark UI. Once Spark is running, navigate to http://localhost 4040 in your web browser, and you'll find all active applications, their states, and even the configuration parameters. Monitoring this UI allows for immediate verification and helps foster an understanding of how Spark is utilizing your set configurations. This tool is invaluable. Think of it as the diagnostic display in a car, offering insights into engine performance and fuel economy. It gives you a thorough view of upcoming tasks, job progress, and even potential issues before they escalate into significant problems. As we wrap up our discussion on Spark environmental settings, it's important to remember how these configurations interact within your Spark applications. Just as you wouldn't go on a long road trip without checking your vehicle's tires, oil, and fuel, making sure your Spark environment is correctly configured is essential for smooth sailing on your data journey. By effectively managing variables such as the Java home, local IP, master host configuration, logging locations, and network settings, you can ensure that your Spark applications run efficiently and are easy to debug. These settings are your toolkit, keeping you prepared for whatever data processing tasks you need to tackle. Now that you have a solid understanding of Spark environmental settings, you're well equipped to create robust and effective Spark applications. Always remember that a little extra work in configuring your environment pays off significantly when it all runs smoothly. Stay tuned as we delve into discussions on Spark optimizations and best practices for maximizing performance, ensuring that your journey through the world of PySpark is both efficient and enjoyable. Now let's see how we can implement a basic Spark application that utilizes the Spark SQL package we previously discussed. The command spark submit packages org Apache Spark, Spark SQL2, 12.3.2.0 your application. Py serves as our entry point for executing a Spark program while also integrating the specified package. In this command, the Spark submit utility acts as the launcher of our Spark application. By including the packages flag, we inform Spark to include the specified library, Spark SQL 2.12 version 3.2.0, which is essential for running SQL queries within our PySpark application. The your application, Py, represents the Python script we will be executing. This approach streamlines the process of ensuring that our application has the necessary dependencies without additional configuration steps. Using this command, Spark resolves the requested package, downloads it if it is not already available, and adds it to the class path, enabling us to leverage Spark SQL's powerful data processing capabilities effectively. This systematic installation method ensures that we can focus on developing and executing our data processing tasks with minimal hassle. Now let's see how we can launch the Spark shell with a specific package loaded. By using the command to start the Spark shell, we can dynamically import the sparkmlib library, which is valuable for machine learning tasks. This command not only initializes an interactive Spark environment, but also specifies that the sparkmlib package should be included right from the start. Using the packages flag allows us to directly include this library without additional setup, making the process seamless. Once the shell is running, we can proceed to execute various commands and interact with Spark's features promptly. This convenience is particularly beneficial when experimenting or prototyping, since it eliminates the need for extensive configurations. Therefore, with this command, developers can quickly explore the capabilities of sparkmlib and begin crafting machine learning models without the overhead of managing dependencies separately. This enhances efficiency and allows for a more rapid development cycle, enabling you to focus on writing and testing your machine learning algorithms directly in the Spark environment. Now let's take a look at how we can implement a classification model using the sparkmlib package. We begin by initializing the Spark context, which is essential for any PySpark application, allowing us to interact with the Spark framework. Once the context is set up, we create a simple dataset containing label feature pairs, which will serve as our training data for the logistic regression model. Next, we parallelize this dataset using the Spark context to distribute the data across the available executors, taking advantage of Spark's ability to process data in parallel. Following data preparation, we proceed to train our logistic regression model using stochastic gradient descent (SGD), a popular optimization algorithm for training models. After the model is trained, we move on to making predictions. In this case, we use a new input vector to demonstrate how the trained model can predict outputs based on previously unseen data. Finally, we print the prediction result, allowing us to evaluate the model's performance on the test input. This example illustrates the powerful capabilities of the sparkmlib package in building and deploying machine learning models within the Spark ecosystem. Now let's implement a command that helps us manage package installations effectively within Spark. Here we'll use the Spark submit command with the packages flag to specify which packages our Spark application should utilize during execution. This command is a vital part of the Spark ecosystem since it enables us to extend our applications with additional libraries, such as Spark SQL or sparkmlib, by simply referencing their group ID, artifact ID, and version. In practice, when we run this command, Spark actively checks its repositories for the requested package. If the package is found, it gets downloaded and included in the class path automatically. This process not only simplifies package management, but also supports transitive dependency resolution, meaning that any additional libraries that the specified package requires will also be fetched without further configuration. This efficiency allows developers to focus on building their applications, knowing that necessary dependencies will be handled seamlessly. Thus, with this command, we streamline our application setup while ensuring we have all the required tools at our disposal. Now let's take a look at the POM XML file structure that we will use to package our Spark application correctly. This XML file is crucial as it defines the project metadata, including the group ID, artifact ID, and version of your project, which is essential for Maven to manage the building process effectively. In this example, we have specified the group ID as ComExample, the artifact ID as MySpark package, and the version as 100. Within the dependencies section, we declare the libraries that our project needs. In this instance, we've included the Spark core library, which is fundamental for any Spark application. This dependency is necessary because almost all Spark applications require core functionality provided by Spark, including data processing and task scheduling. The specific version mentioned here is 3.2.0, ensuring compatibility with our Spark installation. By using Apache Maven to package our code, you can easily organize your project, simplify dependency management, and maintain structured builds. Once this file is set up, you would run the mvn package command, which compiles your code, resolves the dependencies listed, and generates a jar file in the target directory, making it ready for deployment alongside your Spark applications. To wrap it up, managing and installing packages in Spark is a crucial skill that lets you leverage existing functionalities and rapidly develop powerful applications. We've seen how to install packages using Spark Submit, how to check installed packages, and methods for dealing with packages not found in the default repositories. It's all about extending the capabilities of your Spark applications through effective package management. Remember, managing your packages effectively can save you a great deal of time and ensure that your applications run smoothly without unnecessary hiccups. As you venture further into the world of Spark, this knowledge will enable you to tap into a vast array of libraries and tools that can enhance your data processing capabilities enormously. In the upcoming lessons, we'll explore Spark's optimization techniques and how to utilize these packages to further boost your application's performance. So stay tuned, stay curious, and keep experimenting. Monitoring Spark applications is essential for understanding performance and resource utilization. In a world where data processing is crucial for business intelligence and analytics, effectively monitoring the performance of your Spark applications can make or break your success. Good monitoring minimizes bottlenecks, maximizes efficiency, and ultimately enhances user satisfaction. Today, we're going to dive deep into the various aspects of Spark performance monitoring, providing you with the knowledge and practical tools to keep your applications running smoothly. So far, we learned about Spark package management and installation, emphasizing the importance of configuring Spark environmental settings and managing dependencies. We explored how to download and install packages using the Spark Submit command, including a practical example of integrating the Spark SQL and Spark Mlib libraries and applications. Additionally, we discussed methods for verifying and managing installed packages and building custom packages. This foundational knowledge prepares us for optimizing Spark's performance in future lessons. Now we will cover the various techniques and tools used for monitoring Spark applications. To start, let's talk about the Spark UI, which serves as your dashboard for monitoring Spark applications. The Spark UI provides a rich, interactive view of the applications running on your Spark cluster. You can access the Spark UI by navigating to the URL of the Spark master node, typically at http://masternode 8080. Once you're in, you can view active applications, completed jobs, and various metrics that are critical to understanding resource utilization. Within the Spark UI, you'll find several tabs: Jobs, Stages, Storage, Environment, and Executors. The Jobs tab displays a list of executed jobs along with their duration, status, and the stages they invoked. This information is invaluable for identifying which jobs are taking longer than expected. Each job can be broken down into stages, and clicking on these stages provides insight into specific tasks executed and their resource consumption. Now let's implement the following code to monitor task durations in a Spark application. First, we begin by importing the necessary Spark session from the PySpark library, which serves as the entry point to use Spark functionalities. We initialize a Spark session with a descriptive application name, Performance Monitoring Example. This name will help identify our application in the Spark UI. Next, we load a large dataset using the CSV format. The header equals true argument indicates that the first row of the CSV file contains column names, while infer schema equals true allows Spark to automatically determine the data types of the columns. This aids in accurate processing. Following that, we perform a transformation using the groupBy method, which aggregates data based on a specified column while summing up values from another column. This transformation is essential for analyzing our data while leveraging Spark's powerful distributed processing capabilities. Finally, we trigger the execution of our transformations by calling the collect action. This command retrieves the results and brings them into memory, allowing us to interact with the data directly. Monitoring these executions in the Spark UI will help us identify any potential performance issues related to task duration. Now let's implement the following code to optimize our data structure using Spark's built-in types. By defining a schema for our data frame, we can ensure that the data types are set appropriately, which can significantly reduce memory overhead. In this snippet, we first import the necessary classes from PySpark SQL types such as struct type, struct field, string type, and integer type, which are essential for creating a structured schema. Next, we define a schema named schema that consists of two fields, id of type integer type and name of type string type. This structure clearly outlines the expected data types of the columns, which helps Spark optimize how data is stored and processed. Following this, we use the define schema to read a CSV file named optimized dataset (CSV) into a data frame. By explicitly specifying the schema during the read operation, we can avoid the overhead of type inference, which can be computationally expensive. This practice not only leads to better memory management, but also enhances the performance of our Spark application, ensuring efficient resource utilization. Now let's see how we can implement monitoring for our Spark application using Graphite for metrics visualization. The command to execute is the Spark submit command, which allows you to submit your application to the Spark cluster while also configuring the metrics you want to monitor. By adding the conf Spark metrics, conf equals metrics properties option, we instruct Spark to use a specific configuration file, metrics properties, where we define the details of the metrics collection and reporting. This step is crucial as it sets up your application to track important performance indicators such as CPU usage, memory consumption, and task execution metrics in real time. Using this command ensures that your Spark application is not just running efficiently, but it's also providing valuable insights into its performance. With the correct setup, you can proactively identify bottlenecks and adjust your configurations or resource allocations to optimize overall performance. This is a key aspect of maintaining robust operations in a production environment, ensuring reliable performance as your data processing needs evolve. Now let's take a look at how we can effectively monitor Spark application logs in real time. The command provided allows us to stream log output continuously from the specified log files, which can be vital for identifying issues as they occur during the execution of your Spark jobs. Specifically, the command tail fpath//spark/logs/spark out continuously reads the last lines of log files that match the pattern, updating the output as new log entries are written. By utilizing this command, you can observe critical events such as task failures or executor errors as they happen, enabling you to react quickly to any anomalies. This live logging stream is particularly beneficial during debugging, as it provides immediate feedback on the health and status of your Spark applications. Integration with visualization tools like Elasticsearch and Kibana can further enhance this logging process, allowing for more structured analysis of log data. Overall, this command represents a straightforward yet powerful approach to monitoring your applications, ensuring that you can spot potential issues early and optimize performance. Now let's implement the following code to enable dynamic resource allocation in Spark. This configuration allows Spark to manage its resources efficiently based on the application's needs, which is crucial when workloads vary in intensity. By setting Spark Dynamic Allocation Enabled to True, we activate the Dynamic Resource Allocation feature, enabling Spark to automatically add or remove executors depending on the workload. Next, we specify Spark Dynamic Allocation min executors to define the minimum number of executors Spark should keep available. In this case, we set it to 1, ensuring there's always at least one executor ready to handle any incoming tasks. Additionally, we set Spark Dynamic Allocation max executors to 10, limiting the maximum number of executors that can be dynamically allocated. This upper limit prevents unnecessary resource usage and helps manage the efficiency of the Spark cluster. With these settings in place, Spark can respond to workload spikes by scaling up the executors dynamically, thereby improving resource utilization and performance while avoiding overprovisioning. This proactive approach is vital for maintaining the responsiveness and efficiency of Spark applications as demands change. Now let's take a look at the explain method and how it can be utilized to gain insights into your DataFrame's execution plan. When performance issues arise during Spark jobs, understanding the execution plan can be immensely helpful in diagnosing underlying problems. The explain method breaks down the logical and physical strategies that Spark employs to execute the transformations you have performed on your data frame. By invoking transformed data explain, we can access detailed information about the steps Spark will take to process the data. This output sheds light on the operations involved, revealing aspects like join strategies and shuffle commands that may be contributing to inefficiencies. For instance, identifying unnecessary shuffles can help you optimize data partitioning, while observing the order of operations may highlight where you can improve performance. In essence, utilizing the explain method acts as a critical diagnostic tool in your Spark monitoring toolkit, enabling you to systematically analyze and refine performance as you develop your data processing tasks. In the end, keeping a close eye on Spark's performance metrics, logs, and optimizing configurations is vital for maintaining efficient data processing applications. As you go forward, remember that continuous monitoring and proactive adjustments are key to ensuring that your Spark applications run optimally. In summary, we covered the importance of Spark application performance monitoring, the various components of the Spark UI, memory utilization tactics, dynamic resource allocation, effective debugging techniques, and how to leverage logs and metrics for continuous improvement. Armed with these insights and strategies, you should be well equipped to implement efficient performance monitoring in your own Spark applications. Thank you for joining me in this exploration of Spark performance monitoring. Stay curious, keep experimenting, and watch your data processing efficiency. Managing data efficiently within Spark requires proper strategies for storage and processing. In this lesson, we'll explore effective data management strategies, focusing on optimizing storage, processing, and how to ensure you're getting the most out of your Spark applications. So far, we learned about the significance of monitoring Spark applications for optimal performance and resource utilization. We explored the Spark UI as a key tool for observing job performance, including task durations and memory utilization metrics. Additionally, we discussed debugging techniques and the role of dynamic resource allocation, reinforcing the need for continuous monitoring and proactive adjustments in Spark applications. This foundational knowledge sets the stage for effectively enhancing application performance in our next discussions. Next, we will write the code to demonstrate how to create a Spark session, set up a data frame, and utilize the Parquet format for data storage. First, we instantiate a Spark session, which is essential for any operations involving Spark. This serves as the entry point for all Spark functionalities. Now let's create a sample data frame using a simple dataset containing names and IDs. We define the data as a list of tuples and specify the column names, effectively structuring our data frame. Writing this data frame to a Parquet file is straightforward. We use the write_parquet method to save our data frame to a specified path. This action converts the in-memory Spark data frame into a highly optimized Parquet format, which is beneficial for efficient data processing. After saving, we'll read the Parquet file back into a new data frame using the read_parquet function. This allows us to confirm that our data has been successfully saved and can be efficiently accessed later. Finally, we utilize the show method to display the content of the newly created data frame, illustrating the successful retrieval of our data. This workflow exemplifies effective data management practices within Spark. Now let's see how we can implement partitioning in Spark to optimize our data frame's performance. The code begins with the assumption that a data frame named df has already been created, containing relevant data for our analysis. To partition the data frame, we can use the repartition method, specifying the column by which we want to split the data, in this case, the ID column. This approach is vital, as it allows Spark to distribute the data more evenly across its cluster, thereby improving parallel processing and decreasing shuffle operations during computations. After partitioning the data frame, we then proceed to write the newly created partitioned data frame to disk in Parquet format, which is highly efficient for both storage and accessibility. By saving it in this manner, we leverage the benefits of partitioning not just for performance during processing, but also for optimized future queries, as the data is organized in a way that aligns with our analytical needs. This step exemplifies how effective data management strategies can significantly enhance Spark applications' performance and scalability. Now let's see how we can implement caching in our Spark application to improve performance. Caching is crucial when you have data frames that will be reused in multiple operations, as it allows Spark to hold the data frame in memory rather than recomputing it each time it's needed, which can be resource-intensive. To cache a data frame, we use the cache method, which effectively stores the intermediate data frame in memory. This is particularly beneficial for operations that follow, as it speeds up the execution time significantly. After caching the data frame, we proceed to perform actions on it. In this case, we use the group_by function to group the data by the name column and then use count to aggregate the results. The collect method is called to retrieve the results back to the driver program in an understandable format. Finally, we print the result, which displays the count of occurrences for each name in the data frame. This approach demonstrates how caching can enhance the efficiency of your Spark applications, especially when dealing with frequent access to the same dataset, ultimately helping in managing resources better. Now let's see how we can implement salting to manage data skew effectively. In the first part of the code, we are adding a random salt value to the ID column of our data frame. This is achieved by creating a new column called salt, where a random value between 0 and 4 is generated using the rand function from the PySpark SQL functions. By using the round function, we ensure that the salt value is a whole number. Next, we create a second new column, salted ID, by concatenating the original ID and the salt column with an underscore in between, effectively mixing the skewed keys with these random salt values. This process helps distribute the data more uniformly across partitions, mitigating the performance impact caused by data skew. Following this, the show function is used to display the resulting data frame, allowing us to verify how the new salted IDs appear. Now we will transition to a different approach, bucketing data. This technique allows us to save our data frame in a structured manner by dividing it into a specified number of buckets based on the ID column. By doing so, we enhance query performance since Spark can optimize data retrieval, leading to faster execution times for subsequent queries on this table. Now let's see how we can implement the data overwriting and appending strategies in Spark. First, when you need to replace existing data, such as when refreshing datasets, you can use the overwrite mode. This method writes the new data frame to the specified Parquet file, replacing any previous data within the same location. This approach is vital for scenarios where consistent updates are necessary, ensuring that outdated entries are not retained in the data repository. Next, if you want to add new records to an existing dataset without altering the current data, you should use the append mode. This functionality allows you to add new data seamlessly, making it especially useful for ongoing data ingestion processes where additional records need to be integrated continuously. By employing this mode, you can maintain historical data while ensuring that new entries are captured and stored efficiently. In both cases, ensuring you select the appropriate write mode prevents data loss and ensures the integrity of the data you are managing. Understanding these modes is crucial for effective data management in Spark. Now let's see how we can implement schema evolution in Spark when working with Parquet files. When dealing with evolving datasets, it's essential to maintain the flexibility of your data schema. This is where the merge schema option becomes invaluable. By setting this option to true while reading Parquet files, Spark is capable of merging the schema of the existing data frames with any new columns that may be present in the data files being read. This functionality allows you to add new data columns without disrupting the overall data pipeline, which is critical for maintaining data consistency over time. Using this approach ensures that as your application's data requirements evolve, the underlying infrastructure can adapt smoothly. For example, in a scenario where your data model changes frequently, enabling schema merging allows your Spark application to remain robust and resilient, effortlessly adjusting to new data structures. This capability thus enhances your data pipeline's longevity and reinforces the adaptability of your Spark applications, preparing them to meet future data challenges head-on. Now let's implement the following code to set up Delta Lake in our PySpark environment, which facilitates efficient data management and supports ACID transactions. First, we import necessary functionalities from the Delta library and configure our Spark session. Specifically, we set the application name and include the Delta Spark extensions in the configuration. This is crucial for enabling Delta features that allow us to work with Delta tables seamlessly. Next, we create our Spark session using the configured builder. This session will serve as the main entry point for interacting with our data. After that, we demonstrate how to write a data frame in Delta format by using the write function. The data will be saved in output Delta table. This ensures that our data frame is stored in a format that supports versioning and time travel queries, allowing us to easily manage changes over time. Finally, we show how to read back the stored Delta table. By specifying the format as Delta, we can load the data frame and access our data with all the benefits that Delta Lake offers, ensuring robustness and flexibility in our data workflows. In conclusion, effective data management strategies in Spark revolve around using optimized storage formats, implementing proper partitioning and caching techniques, managing skew, choosing the right write modes, and ensuring schema flexibility. Incorporating modern solutions like Delta Lake extends the possibilities even further, allowing you to maintain the integrity and performance of your data pipelines. As we wrap up this lesson, remember that the success of your data projects often hinges on how well you can manage and optimize your data. Embrace these strategies, and you'll be well prepared to tackle the challenges of big data with Spark. Thanks so much for tuning in, and happy Now let's see how we can read data from HDFS using PySpark. First, we begin by establishing a Spark session, which serves as the entry point for interacting with Spark functionalities. By configuring the session with a specific application name, here labeled Hadoop integration example, we ensure that the application can be identified easily when monitoring Spark jobs. Next, we focus on reading a CSV file stored on HDFS. Using the read CSV method, we provide the HDFS file path denoting the location of the CSV file. The inclusion of the header equals true option allows Spark to automatically use the first row of the CSV as the column names, thus simplifying our data handling. Meanwhile, with infer schema equals true, Spark intelligently determines the appropriate data types for each column, which eliminates the need for manual type definitions. This enhances the ease of working with data since you can directly start analyzing it without cumbersome setup. Lastly, we invoke the show method to display the contents of the data frame created from the CSV file. This insight helps us verify that the data has been loaded correctly and is ready for further processing, demonstrating the seamless integration between Spark and HDFS. Now let's see how we can implement Hive integration within our Spark application. First, we initiate a Spark session using the Spark Session Builder method and set an application name for easy identification. To activate Hive functionalities, we call the Enable Hive Support method, which allows Spark to tap into the Hive metastore for metadata management. This integration is crucial as it enables us to perform SQL-like queries on data managed by Hive. Once our Spark session is set up, we can proceed to query Hive tables. The SQL method is employed for executing a SQL query, allowing us to interact with the data stored in Hive. In this example, we query all records from a specific Hive table named Hive Table, demonstrating how Spark seamlessly accesses this data. Finally, we use the show method to display the results in a tabular format, making it easy to analyze the data directly from Hive. This integration not only enhances Spark's capabilities, but also leverages Hive's scalable storage, facilitating complex data analysis with ease. Next, we will implement the integration between Spark and Kafka, a powerful combination for processing real-time streaming data. To begin, we establish a Spark session, which acts as the entry point for our application and enables us to leverage Spark's functionalities. Now let's see how we can create a streaming data frame that connects to a Kafka broker. We specify the format as Kafka and set the Bootstrap server option to point to our local Kafka instance. By subscribing to a designated topic, we can continuously read messages being published to Kafka. This streaming data frame serves as a source of live data that we can manipulate on the fly. Next, we will process this stream by applying transformations to the data. We utilize the selectExpr method to cast the Kafka message key and value to strings. This casting is crucial as it prepares the data for subsequent analysis or transformations, ensuring we can handle it effectively in our Spark application. By structuring the data in this way, we set a solid foundation for developing real-time analytics with Spark and Kafka. Now let's see how we can write the process streaming data back to the console for testing purposes. The code begins by defining a streaming query using the writeStream method on our process data frame, which is processStreamDF. This method is configured to operate in append mode, ensuring that new rows are added to the output every time the stream receives new data. The format console specifies that the output will be displayed directly in the console, which is invaluable for debugging and monitoring real-time data processing. After setting up the query parameters, we invoke start to initiate the streaming query, which begins the continuous flow of processed data to the console. Finally, the query wait termination call is crucial, as it causes the application to wait and remain active until it's explicitly terminated. This means that the application keeps running, allowing you to see the incoming data in real time until you choose to stop the execution. This setup highlights the capability of Spark to handle real-time data streams effectively, providing immediate insights as data flows in. Next, we will write the following code to demonstrate how Spark can facilitate batch processing of data before passing it to Flink for real-time analytics. First, we will read a CSV file named input data CSV into a Spark data frame using the read CSV method. This method allows us to seamlessly load structured data and prepare it for further analysis or processing. After loading the data, we will write the contents of the data frame to a Parquet file, process data Parquet, which provides a highly efficient columnar storage format optimized for performance. Parquet not only reduces the file size but also improves read and write times for large datasets, making it an excellent choice for big data applications. Once this batch processing is completed in Spark, the next step involves integrating with Flink. In the code, there's a placeholder where we would implement a Flink job to consume the Parquet data and perform real-time analytics. This integration showcases how Spark's powerful batch processing capabilities can be effectively combined with Flink's advanced stream processing to create a comprehensive big data solution that caters to both batch and real-time data needs. Now let's implement the following code to demonstrate how to integrate Spark with TensorFlow for machine learning tasks. We start by initializing a Spark session, which is essential for any Spark application as it allows us to interact with the Spark framework. Once the session is established, we use Spark to read a CSV data file, automatically inferring the header and schema, which simplifies our data handling. After loading the data into a Spark data frame, we convert this data frame to a Pandas data frame to make it compatible for TensorFlow model training. This conversion allows us to leverage Spark's powerful data processing capabilities while utilizing TensorFlow's advanced neural network functionalities. Next, we build a simple neural network using TensorFlow's Keras API. The model consists of a dense layer with RayLU activation, followed by an output layer with a sigmoid activation function, which is suitable for binary classification tasks. We then compile the model, specifying Atom as the optimizer and binary cross-entropy as the loss function. Finally, we train the model using the feature and target data from our processed Pandas data frame, iterating over 10 epochs. This workflow effectively demonstrates how to harness the strengths of Spark and TensorFlow in a cohesive machine learning pipeline. Now let's see how we can implement Spark to read data directly from an Amazon S3 bucket, harnessing the power of cloud storage. We begin by creating a Spark session, which initializes the application and allows us to interact with the Spark infrastructure. With the Spark Session Builder method, we set the application's name to AWS S3 integration example and call getOrCreate to either retrieve an existing session or create a new one. Next, we employ the Spark read CSV method to read data stored in a CSV file located in our specified S3 bucket. By providing the S3 path and setting the parameters, header equals true to utilize the first row as column names and infer schema equals true to automatically detect data types, we make it easy to handle the dataset without manual adjustments. Finally, we invoke S3df show to display the contents of the data frame, giving us a quick overview of the data we've just loaded. This approach exemplifies how integrating Spark with cloud services can streamline data access and processing, making big data workflows more efficient and scalable. Now let's see how we can integrate Spark with R using the Sparkler package, which allows data scientists familiar with R to leverage Spark's distributed computing capabilities effectively. First, we begin by establishing a connection to a Spark cluster using the Spark Connect function, where we specify the cluster's master URL. In this case, we're using local to signify a local Spark instance. Next, we read data from a CSV file into a Spark data frame employing the Spark read CSV function. Here, we specify the name of the resulting Spark data frame and the path to the input CSV file, while also indicating that the first row contains headers, which helps in correctly interpreting the data structure. After successfully loading our data, we seamlessly transition into data manipulation. We use the familiar deepler syntax to filter the data frame based on specific criteria, enabling us to work efficiently with the data. As we would in R, the filtered results are then collected back into R for further analysis or visualization, bridging the gap between Spark's scalability and R's analytical capabilities. This powerful integration empowers R users to handle large datasets effectively while utilizing their favorite tools. As we recap the integration of Spark with various frameworks, it's crucial to remember the benefits of these synergies. They not only enhance the capabilities of Spark, but also optimize performance and enable diverse applications. From integrating with Hadoop's HDFS for reliable storage, to querying Hive tables with Spark SQL, to dealing with real-time data streams from Kafka, and even working with powerful machine learning libraries like TensorFlow, the potential is virtually limitless. Every integration option opens up pathways for simpler architectures, faster processing, and ultimately, better insights from your data. As we transition into our next topics, feel empowered by the knowledge that integrating different frameworks with Spark allows you to adapt to any data challenge that comes your way. With the right combinations and strategies, you can create a tailored big data solution that meets your unique analytics needs. Happy The development of Apache Spark is rapidly evolving, with a focus on enhancing machine learning capabilities and seamless cloud integration. In this lesson, we will dive into future trends in Spark development, exploring how these advancements can shape big data applications and AI-driven solutions. So far, we have learned about the effective integration of Spark with frameworks such as Hadoop, Hive, and Kafka, which enhances big data applications by leveraging their strengths for storage, querying, and real-time data processing. We explored how to read data from HDFS and Hive, as well as how to set up a streaming DataFrame with Kafka for real-time analytics. Additionally, we discussed the advantages of combining Spark with machine learning frameworks and cloud platforms for scalable processing. Today, we will cover the future trends in Spark development, focusing on the expansion of machine learning capabilities, improved performance in cloud environments, and the integration of advanced technologies like edge computing and serverless architectures. Now let's see how we can implement a machine learning pipeline using PySpark and mlib. First, we initiate a Spark session, which is essential for operating within a Spark application. With this session established, we move on to create a sample dataset using a data frame, structured with an ID, labels, and features. This serves as the input data for our model. Next, we focus on feature engineering by using the vector assembler, which integrates multiple feature columns into a single vector column called features. This is a crucial step as machine learning models in Spark typically require input data to be in vector form. Following that, we specify our machine learning model, in this case, a random forest classifier, which is a popular choice for classification tasks. Here, we set the label and features columns and define the number of trees for the ensemble method. Finally, we create a pipeline that chains together the vector assembly and classifier stages, streamlining the process. By fitting the pipeline to our sample data, we efficiently train the model, allowing us to simplify the workflow and enhance manageability in our machine learning tasks. Now let's see how we can implement a simple Spark application that reads data from an Amazon S3 bucket and performs basic transformations. First, we create a Spark session, which is the entry point to any Spark application. This is where we specify the application name and ensure that we can harness the full capabilities of Spark. Next, we focus on reading data. We utilize the built-in Spark read CSV method, specifying the S3 path to our dataset. By enabling the header option, we ensure that the first row is interpreted as column names, and the infer schema option allows Spark to automatically determine the data types of each column for easier manipulation. This step retrieves our data into a data frame called S3DF, which acts like a table in Spark, making data operations straightforward and efficient. Once the data is loaded, we can examine it using the show method, which displays the first few rows of the data frame. This provides a glimpse into our raw data. Moving forward, we apply a basic transformation by grouping the data based on a specified column and counting the occurrences stored in a new data frame called results. Finally, we again use the show method to visualize the grouped results. This entire flow highlights the power and simplicity of using Spark for data processing in a cloud-integrated environment. Now let's implement a Spark job that operates in a serverless environment, responding to events like new data arrivals in a cloud storage bucket. In this example, we start by creating a Spark session with a designated application name, which initializes the Spark functionality we need for processing data. Next, we define a function named processData, which takes event and context as parameters. The event is expected to contain a path to the data file stored in cloud storage, enabling our job to react to incoming data dynamically. We then read the data as a data frame using Spark's CSV reader, automatically inferring the schema and reading the header. After loading the data, we perform a transformation by grouping the data based on a specified column and counting the occurrences. Finally, we save the results back to S3 in CSV format. This approach illustrates how serverless architectures can enhance data processing flexibility, allowing developers to focus on logic without managing infrastructure, making it a powerful model for modern applications. Now let's see how we can implement a real-time data processing scenario using Apache Spark in an edge computing context. In this code snippet, we begin by establishing a Spark session, which is critical for any Spark application as it serves as the entry point for all functionality. Next, the code creates a data frame representing a simulated data stream from a socket, where the data points are expected to arrive in real time. This is done using the readstream method, specifying the format as socket along with the host and port number. The data stream is then processed by grouping the incoming data by sensorid and calculating the average value associated with each sensor. This aggregation enables quick insights into the data being collected from different sensors. Finally, the process stream is written back to the console in real time using write_stream. By setting the output mode to update, the application ensures that any new calculations reflect immediately, allowing operators to respond swiftly to changes in the sensor data. This setup illustrates Spark's powerful capabilities for real-time analytics, making it suitable for various applications in industrial and IoT environments. Now let's take a look at a practical example that showcases how to visualize data from a Spark DataFrame using Python's matplotlib library. First, we initiate a Spark session, which provides the necessary context for running Spark jobs. After establishing the session, we read data from a CSV file located in an S3 bucket. This step is crucial as it allows us to import the dataset into Spark for analysis. Once the data is loaded, we utilize the group_by method to aggregate the data based on a specific column, in this case, category, and then count the occurrences. This summary is then converted to a pandas data frame, which is convenient for visualization. Next, we create a bar plot using matplotlib to depict the summary visually. The plot displays the categories along the x-axis and their corresponding counts on the y-axis, providing a clear and intuitive representation of the data distribution. Finally, we title the plot and label the axes appropriately before displaying the results. Through this example, we see how leveraging Spark's capabilities alongside powerful visualization tools like matplotlib can enhance our ability to analyze and interpret large datasets effectively. In conclusion, the future trends in Spark development are promising, with significant advancements that will enhance machine learning capabilities, improve cloud integration, and incorporate modern technologies like edge computing and serverless architectures. As we embrace these trends, we can expect Spark to become an even more powerful tool in the big data toolkit, driving innovation and efficiencies across various fields. Not only will these advancements make data processing faster and simpler, but they will also ensure that Spark remains at the forefront of the data analytics landscape. As we move forward, it's essential to stay tuned to these developments in the Spark ecosystem. Whether you're a data engineer, data scientist, or software developer, understanding these future trends will equip you with the knowledge needed to leverage Spark efficiently in your projects. The journey of Apache Spark is just beginning, and we are fortunate to witness its evolution shaping the future of data processing and analysis. Let's embrace this evolution and prepare for the exciting possibilities. To deploy your Spark application, you need to choose the appropriate mode of deployment based on your use case. Apache Spark offers various deployment strategies tailored to different operational needs. Throughout this lesson, we will dive deep into these strategies, enabling you to understand how to deploy Spark applications effectively and efficiently. So far, we learned about the rapid evolution of Apache Spark, focusing on enhanced machine learning capabilities and improved cloud integration. We explored effective integrations with frameworks like Hadoop, Hive, and Kafka, alongside practical examples demonstrating data processing and real-time analytics. Additionally, we discussed the future trends of Spark development, including AutoML functionalities, serverless architectures, and the incorporation of edge computing technologies. These advancements aim to simplify data workflows, enhance performance, and empower users in the evolving data landscape. Now we will cover Spark application deployment strategies, focusing on how to adapt your deployment approach based on specific use cases and environments. Now let's take a look at how we can create a simple Spark application in local mode using PySpark. First, we start by importing the Spark session class from the PySpark SQL module. This class is pivotal as it serves as the entry point for programming Spark with DataFrame and SQL functionality. Next, we instantiate a Spark session with a specified application name, local app, and set the master to local asterisk. This configuration allows Spark to utilize all available cores on our machine, making it ideal for testing and development purposes. Once the session is created, we can proceed to create a data frame, which in this case will contain 3 records with names and IDs. We define our data as a list of tuples and pass it to the createDataFrame method of the Spark session along with the corresponding column names. After the data frame is successfully created, we utilize the show method to display the contents of the data frame, which provides a quick visual inspection of our data. Finally, we stop the Spark session to release the resources. This simple application highlights the ease of developing Spark code locally, making it straightforward to prototype and test without requiring a cluster setup. Now let's see how we can set up a standalone Spark cluster by starting the master and worker nodes. The first command initiates the master node using a shell script provided by Spark, which coordinates the resources across the cluster. This master node acts as the central point that helps distribute tasks to the worker nodes efficiently. Next, we start the worker nodes by executing another command, replacing master IP with the actual IP address of your master node. This command connects each worker node to the master, allowing them to receive and execute tasks. After establishing the cluster with these commands, we will move on to submitting our Spark applications to the standalone cluster. To do this, we use the Spark submit command. This command includes parameters such as class to specify the main class of your application and master, which directs Spark to the master node we just initiated. By including your application, jar, we define the application package to be executed. This process demonstrates how to effectively label our work so that Spark can manage the execution seamlessly across the cluster's resources. Now let's see how we can create a Spark cluster using AWS EMR, which simplifies the deployment of Spark applications. The command starts with emr create cluster, indicating that we want to initiate a new EMR cluster specifically for running Spark jobs. The name flag allows us to assign a unique name to the cluster, making it easier to identify in the AWS Management Console. Next, we specify the release label, which in this case is set to EMR530.0. This indicates the version of Amazon EMR we want to use, ensuring compatibility with the features and applications needed. Following that, we use the applications flag to define the software to install on the cluster. In this example, we are installing Spark. We also provide EC2 instance attributes with the EC2 attributes flag, where we specify a key pair using key name equals your key pair. This key pair is crucial for SSH access to the instances. Additionally, we select the instance type with instance type M5 X large, which determines the compute power available, and define the instance count as 3, indicating how many instances will be active in the cluster. Finally, using useDefault roles allows the cluster to run with the default IAM roles, streamlining the setup process. This command equips your environment with the necessary resources to run Spark efficiently while minimizing the complexity of infrastructure management. Now let's see how we can implement a Spark job in a Kubernetes environment. The command begins with kubectl run, which is used to create a new pod in Kubernetes. Here we specify our application name, your Spark app, followed by the image that contains our Spark application, indicated by image equals your Spark image. This image is crucial as it bundles our application along with all its dependencies, ensuring consistency across different environments. Next, we use the to indicate that the following options are for the application itself, in this case, Spark submit. The master argument specifies the master URL for the Kubernetes cluster where our Spark application will run. We point to the Kubernetes master IP using k8//https//kubemaster IP. The deploy mode cluster option indicates that the driver will run inside the Kubernetes cluster, allowing for better resource management and scaling. Finally, we define the application name with name your Spark app, specify the main entry class of the application with class main class, and point to the jar file of the application with your application, jar. This setup enables seamless execution of Spark jobs alongside other containerized services, leveraging Kubernetes orchestration capabilities for enhanced scalability and management. Next, we will write the following code to adjust our Spark configurations for optimal resource utilization. This code snippet demonstrates how to set the memory and CPU cores for each executor in your Spark application. By using the Spark session builder, we start by naming our application config example, which will help us identify it later in logs and monitoring tools. The two config methods play a crucial role. The first sets Spark executor memory to 2G, allocating 2 GB of memory to each executor. This is important because sufficient memory ensures that your application can handle larger datasets without running into out-of-memory errors. The second configuration, Spark executor cores, is set to 2, which assigns 2 CPU cores per executor. Properly tuning the number of cores allows for parallel processing, which is key to enhancing performance and reducing computation times. After applying these configurations, we invoke get_create to either retrieve an existing Spark session or create a new one with the specified settings. This careful configuration enables Spark to efficiently process workloads while optimizing available resources, leading to smoother operations overall. Moreover, understanding the networking aspect of Spark deployment is essential. Depending on the infrastructure, network bottlenecks can significantly influence data transfer speeds, especially for shuffled data. Thus, ensuring the right network configuration and choosing the appropriate resource allocation plays a pivotal role in effective deployment. In conclusion, deploying your Spark application requires careful consideration of the deployment mode that best suits your use case. Whether you are choosing local mode for development, standalone mode for a small cluster, cloud services for scalability, or Kubernetes for a containerized approach, understanding these modes and how to tune them is crucial. By doing this, you will pave the way for more efficient, faster, and reliable Spark applications. In our upcoming tutorial, we will dive deeper into troubleshooting common Spark deployment issues, optimizing performance further, and best practices for maintaining a healthy Spark application. Error handling in Spark can be complex due to its distributed nature, thus, it requires careful consideration of various factors. In this lesson, we will delve into advanced error handling techniques within Apache Spark applications, focusing on how to effectively manage exceptions and ensure robust application performance. So far, we learned about the various deployment strategies for Apache Spark applications, including local, standalone, cloud, and Kubernetes modes. Each mode has its unique advantages suited to different use cases, from development to scalable cloud solutions. We also touched on the importance of configuration and resource management for optimal performance, alongside considerations for networking and deployments. Now we will talk about advanced error handling techniques in Spark that will enhance the robustness of your applications. Now let's take a look at how we can implement a transformation that demonstrates error handling in Spark. We begin by importing the Spark context from the PySpark library and initializing a Spark context with a specific application name. Next, we create a resilient distributed dataset (RDD) containing a set of integer values. This RDD represents our data source for subsequent transformations. Following this, we write a transformation using the map function, which applies a lambda function to each element in the RDD. In this case, the lambda function attempts to divide the number 10 by the difference between each element and the number 3. It is important to note that this transformation introduces the potential for a zero division error, particularly when the element value is 3. However, because Spark transformations are lazy, this error will not be triggered immediately. The actual execution and consequently the error occurs when we call collect on the transformation. This action triggers the computation of the RDD and surfaces any errors encountered during processing. By recognizing this behavior, we can strategically design our error handling approach. Now let's see how we can implement a safe division function using error handling techniques in Spark. The function safe division is designed to perform a division operation while gracefully handling any potential division by zero errors. Inside the function, we utilize a try except block. The try section executes the division, and if a zero division error occurs, the except block is invoked, returning none instead of terminating the job. This approach ensures that the transformation continues running, even when individual records might cause issues. Next, we apply this safe division method to an RDD through the map transformation. This allows us to process each element of the RDD using the safe division function. The results are collected using the collect action, which triggers the computation. By using this method, we enhance the robustness of our Spark job, allowing it to handle problematic records without failing entirely. This technique illustrates an effective way to manage exceptions, particularly for transformations that may encounter bad data. Now let's see how we can implement a retry mechanism for our data loading operations in Spark. In the provided code, we utilize the retrying library to handle transient errors that may occur when connecting to external systems, such as databases. The load data function is decorated with the @retry decorator, which specifies that the function should attempt to execute a maximum of 3 times, waiting 2 seconds between each attempt if a failure occurs. Inside this function, we simulate a transient database connection error by raising an exception, which demonstrates how the retry mechanism would trigger. This approach is particularly useful in unpredictable environments where network issues might cause temporary failures. The try except block surrounding the function call captures any exceptions that persist after the retries are exhausted, allowing us to print a friendly error message. This not only improves the robustness of our Spark application, but also enhances user experience by preventing abrupt crashes during data loading operations. By effectively implementing retries, we can ensure that our application handles intermittent failures gracefully. Now let's implement a demonstration of handling task-level failures in Spark using accumulators. In this scenario, we initialize a Spark context and create an accumulator named FailureCount that tracks how many times we trigger a failure intentionally during processing. The processing function, processData, is designed to simulate a failure by raising an exception when the input value is 2. Each time this intentional failure occurs, the accumulator is incremented, allowing us to count the number of failures. We then set up an RDD containing a few integers and apply the processData function using the map transformation. Unlike immediate execution, transformations in Spark are lazy, meaning they only compute results when an action is triggered. For this example, we use the collect action, which gathers results back to the driver program. If an exception is raised during processing, we handle it with a try-except block, ensuring the job does not fail completely. Finally, we print the total number of failures encountered, which provides valuable insight into the effectiveness of our error handling strategy. This mechanism is essential for diagnosing issues and making our Spark applications more resilient. Now let's implement proper logging in our Spark job to effectively track any errors that arise during processing. We begin by importing the necessary logging module and initializing a Spark context. Setting up logging is crucial. Here, we configure the logging level to capture errors, which will allow us to log useful information when something goes wrong. Next, we define a function called processWithLogging, which attempts to perform a division operation while also trapping potential division by 0 errors. If a 0 division error occurs, instead of failing silently or crashing the job, we log an error message. This message includes the specific value that caused the error and the error details itself, which enhances our understanding during debugging sessions. We then create an RDD from a list of integers and apply our function using the map transformation. Finally, we collect the results. This implementation not only facilitates error tracking, but also ensures that the job continues running despite encountering errors. By employing logging in this manner, we can bolster the robustness of our Spark applications, making them better equipped to handle issues that may arise in a production environment. In addition to logging, you can enhance error detection mechanisms by using *Spark's Web UI ***. The Spark UI provides insights into job execution, including tasks that failed and their associated logs. You can access the Spark UI typically on localhost 4040 in local mode, which gives you a visual representation of your job's execution plan, stages, and tasks. Now let's implement the following code to configure resource allocation in our Spark application. In this snippet, we create a Spark session, which is the entry point for using Spark. It's important to configure the right amount of resources for our application based on the workload and data size. Here, we set the executor memory to 2G and the driver memory to 1G. The Spark executor memory configuration determines how much memory is allocated to each executor, which is crucial for managing the RAM that each distributed task can use during execution. By allocating more memory to the executor, we can help prevent memory-related task failures. Similarly, the Spark driver memory setting specifies how much memory the driver program, which coordinates the Spark application's execution, will utilize. With appropriate configurations in place, we can significantly reduce the likelihood of failures caused by resource exhaustion. This proactive approach to resource management ensures that our tasks will have enough memory to run efficiently and ultimately leads to better application performance in a production environment. Finally, it's important to have a solid understanding of *** best practices for debugging * errors in Spark applications. A methodical approach to debugging includes breaking down your jobs into smaller units of work, enabling precise isolation of the pitfalls. By testing transformations and actions incrementally, you can more effectively pinpoint errors. Consider first running your transformations on reduced datasets to ensure correctness before scaling them up to the full dataset. This staged approach not only helps in error detection, but also speeds up development cycles. In conclusion, advanced error handling in Spark is an essential skill for anyone looking to build robust data applications. By understanding the distributed nature of Spark, employing try-except blocks, utilizing retries, logging errors effectively, and tuning configurations, you can create resilient Spark applications capable of handling various error scenarios. In the next lesson, we will shift gears towards troubleshooting techniques and best practices for maintaining Spark applications, helping you ensure that your solutions not only work but thrive in production environments. Integrating Spark with external data sources is one of its standout features that empowers users to build scalable data processing pipelines. Today, we're going to explore how Spark provides multiple connectors to seamlessly connect with various data sources like HDFS, S3, and many popular databases. So far, we've learned about the complexities of error handling in Apache Spark due to its distributed nature. We explored the distinction between transformations and actions, emphasizing the need to handle errors that emerge during execution. Additionally, we discussed the importance of using try-except blocks, implementing retries, and utilizing logging mechanisms to ensure robust applications. Moving forward, we will focus on integrating Spark with external data sources, illustrating how to connect, read from, and write to these sources effectively. Now let's take a look at how to read a file stored in HDFS using Spark. We begin by importing the necessary Spark context from the PySpark library, which is essential for initializing a Spark application. Afterward, we create an instance of Spark context, naming our application HDFS read example. This context serves as the entry point for all Spark functionality. Next, we specify the HDFS file path, ensuring it's correctly formatted to include the name, node address, and port, along with the specific path to the file we want to read. With the path defined, we utilize the text file method of our Spark context to read the text file located at the specified HDFS path. This method returns an RDD, resilient distributed dataset, which is a foundational data structure in Spark designed for distributed processing. Finally, we call the collect action on the RDD. This action pulls all the data from the distributed nodes back to the driver program, allowing us to print the contents. It's crucial to replace the placeholder values in the HDFS path with your actual configurations to ensure the code functions correctly. This straightforward approach illustrates how Spark provides powerful capabilities for handling large datasets in a distributed manner. Now let's see how we can implement reading a CSV file stored on Amazon S3 using Spark. We start by importing the Spark session, which is essential for creating data frames in Spark applications. This is achieved by calling Spark Session Builder and setting the application name to S3 read example. This method, getOrCreate, initializes the Spark session, allowing us to proceed with our data operations. Next, we specify the S3 path where our CSV file is located, replacing your bucket name /path/ to /s3/file CSV with the actual path to your file in S3. With the path defined, we can use the Spark read CSV method to read the data. Here we set header equals true to indicate that the first row contains the column headers, ensuring that Spark interprets the data structure correctly. Additionally, infer schema equals true automatically infers the data type of each column, which simplifies our data processing efforts. Finally, we utilize df_show to display the contents of the data frame in a tabular format. This not only helps us verify that we have correctly loaded the data, but also serves as a confirmation of our successful integration with S3, demonstrating the ease of working with data in Spark. Now let's see how we can implement a connection to a MySQL database using Apache Spark. The first step is to define a JDBC URL that specifies the database location and select our database of interest. In this case, we include the database URL, port number, and name to establish the connection. Next, we will create a properties dictionary that contains the necessary credentials, such as the username and password, ensuring we also specify the JDBC driver to use for MySQL. This structured approach secures our application by centralizing connection details. Now let's define a SQL query to select the data we need from the desired table, labeling it appropriately to facilitate operations within Spark. Following this, we will use the Spark read JDBC method, where we'll pass the connection URL, the SQL query, and our authentication properties. This function effectively retrieves data from the MySQL database and converts it into a Spark data frame, which is a powerful data structure for processing and analyzing data in Spark. Finally, using df_mysql_show, we will visualize the data to confirm that the connection and query executed successfully, setting the groundwork for further analysis and transformations. Now let's implement the following code to write our data frame back to S3 in a Parquet format. Here, we first define the output path for our Parquet file, which specifies the S3 bucket and the desired directory structure. It's essential to replace your bucket name and the path components to suit your specific S3 setup. Next, we utilize the write method available on the DataFrame df-mysql, indicating that we wish to persist the processed data. By chaining the mode overwrite function, we instruct Spark to overwrite any existing data at the output location. This feature is particularly useful when our processed data needs to be updated without retaining old versions. Finally, the parquet output S3 path method completes the command, signifying the format in which we want to save our data frame. Parquet is a highly efficient columnar storage format, optimized for performance. This seamless interaction with S3 not only aids in efficient data storage, but also enhances data accessibility for future processing tasks, making our data pipeline robust and adaptable. Now let's see how we can implement the process of reading a large dataset from a MySQL database using Apache Spark with optimal performance in mind. In this example, we leverage the Spark read JDBC method, which allows us to connect to the database via JDBC. By specifying parameters such as URL, table, and properties, we ensure a secure connection to our MySQL database with the necessary credentials. To enhance performance, we introduce partitioning into the read operation. By setting num partitions to 10, we are instructing Spark to split the query into 10 parallel tasks, effectively utilizing multiple threads to fetch data simultaneously. The partition column parameter indicates the specific column we are using to divide the data, which in this case is the id column. We also define the lower bound and upper bound to limit the range of values that the partitioning column can take, further optimizing the data retrieval process. This approach allows for faster read times, particularly when dealing with extensive datasets, resulting in a more efficient data processing pipeline. Next, we will write a function to fetch sensitive information securely, such as database credentials, using AWS Secrets Manager. This approach helps ensure that sensitive data isn't hard-coded into our scripts, enhancing security and compliance. In the code, we begin by importing the necessary Boto3 library, which allows us to interact with AWS services, and the Spark Session class from PySpark, which is essential for creating a Spark application context. We then define a function called getSecret. Inside this function, we create a client for the AWS Secrets Manager service. The secret name variable holds the name of the secret we wish to retrieve. Using the client, we call the getSecretValue method, providing the secret name to fetch its value securely. The function then returns the secret as a string. After defining the function, we invoke it to fetch the database credentials and store them in the variable dbCredentials. These credentials can now be used to establish a connection with the database without exposing sensitive information in the source code, adhering to best practices for managing sensitive data in your Spark jobs. As we step closer to wrapping up, it's crucial to remember that monitoring and managing your Spark applications effectively plays a significant role when it comes to integrating with external data sources. You need to handle scenarios where data is updated or deleted in external tables while your Spark job is running. Consider scenarios such as race conditions where data might change in your database while you are reading from it. An effective strategy here is to implement a polling mechanism that periodically checks if the data source has been updated, which could be complemented with watermarking strategy if necessary. Additionally, tuning Spark's configurations related to data fetching and caching can enhance performance and consistency. In conclusion, integrating Spark with external data sources like HDFS, S3, and various databases opens up a plethora of possibilities for data processing and analysis. We've explored how to read and write data seamlessly from these sources, which empowers you to create robust data pipelines. So the next time you work with Spark, remember the versatility of connectors available and don't hesitate to experiment with different data sources. In our next session, we'll dig deeper into troubleshooting techniques and best practices for maintaining Spark applications in production environments, ensuring your workflows are not only efficient but also resilient. Thanks for tuning in and happy. Leveraging Apache Spark for advanced machine learning capabilities helps to enhance data analysis workflows dramatically. In today's fast-paced data-driven environment, the ability to analyze massive datasets efficiently and effectively is paramount. We will explore some advanced machine learning techniques that can be applied using Spark, specifically with PySpark, to elevate your data analysis game. So far, we covered integrating Spark with external data sources such as HDFS, S3, and various databases, enabling the construction of scalable data processing pipelines. We also focused on reading from and writing to these sources and discussed performance optimization and security practices. Furthermore, error handling and monitoring strategies were emphasized to ensure the robustness of Spark applications during data integration. Now we will cover advanced machine learning techniques in Spark and how to apply them to enhance your workflows. Now let's take a look at how to implement a random forest classifier using PySpark, which is an effective ensemble method for improving our predictive performance. First, we create a Spark session to initialize the environment for our application. This is essential to leverage Spark's capabilities, including distributed data processing. Next, we load our dataset from a CSV file, ensuring that the data is correctly interpreted with headers and inferred schemas for data types. After loading the data, we perform feature engineering by using the vector assembler, which combines our specified feature columns into a single vector column named features. This transformation is crucial as the random forest model requires input in a specific format. We then split our dataset into training and test sets using a random split, enabling us to train our model on one portion and evaluate it on another. Following this, we initialize the random forest classifier by defining which column holds the labels and which contains the features. After fitting the model with the training data, we make predictions on the test dataset. Finally, we evaluate the model's accuracy using a multi-class classification evaluator and print the results. This workflow demonstrates the fundamental steps in training a machine learning model with Spark. Now let's see how we can implement a simple convolutional neural network, CNN, for image recognition using TensorFlow within a Spark environment. First, we initiate by creating a Spark session, which is essential for running any Spark application, enabling us to tap into its distributed data processing capabilities. Next, it's important to prepare our data, which should be in NumPy format to be compatible with TensorFlow. The comment in the code reminds us to load the training and label data from NumPy arrays, setting the stage for model training. Following the data preparation, we define the architecture of our CNN using Keras. Our model consists of a convolutional layer that extracts features from images, followed by a max pooling layer to reduce dimensionality. We then flatten the output for the fully connected dense layers, where the first dense layer comprises 128 neurons activated by RayLU, leading to the final layer which uses softmax for multi-class classification. Once our model structure is defined, we compile it with the Atom optimizer and specify the loss function as sparse categorical cross-entropy. This paves the way for training, which we execute for 10 epochs using a batch size of 32. Finally, we save our trained model to a file for future use and evaluate its performance on unseen test data, printing the test accuracy to assess how well it generalizes. Now let's take a look at how we can implement a simple text classification model using TF-IDF and a logistic regression classifier. We begin by creating a Spark session, which acts as the entry point for interacting with Spark functionalities. After setting up, we load our text data from a CSV file, ensuring that it is structured correctly for the model. Next, we define the feature extraction process using hashing TF, which transforms our text data into raw features based on term frequency. This raw feature set is then passed to the IDF estimator to compute the TF-IDF scores, effectively giving us weighted representations of the text that reflect its importance relative to the entire dataset. With our features prepared, we instantiate a logistic regression model, specifying the label column for training. To streamline the workflow, we encapsulate the entire process, feature transformation and model training, within a pipeline. This allows us to fit the model in one go. Finally, after training the model, we generate predictions on the same dataset and evaluate our model's performance by calculating accuracy. This step is crucial, as it helps us understand how well our classifier performs on the given text data. Now let's see how we can implement a recommendation system using the alternating least squares (ALS) algorithm in PySpark, which is ideal for collaborative filtering tasks. We begin by creating a Spark session to enable us to leverage Spark's capabilities for handling large datasets efficiently. The first step is to load the interactions data, which contains past user item interactions. This data is critical as it serves as the foundation for our recommendations. Next, we define the ALS model with specific parameters. Max iter controls the number of iterations, reg param helps prevent overfitting, and we specify the columns representing users, items, and ratings. The cold start strategy set to drop ensures that predictions for unknown users or items are discarded, while the non-negative parameter ensures all predicted ratings are positive, making it suitable for most recommendation scenarios. After defining the model, we train it using our interactions data. This process fine-tunes the model to recognize patterns in user preferences. Once trained, we generate predictions to evaluate how well our model performs on the same dataset. Finally, we use the RMSE metric to assess the model's accuracy, providing insights into the effectiveness of our recommendation system. In summary, Spark's advanced machine learning capabilities offer an impressive toolkit for managing data analysis workflows at scale. We've explored techniques such as ensemble methods with the random forest, deep learning with CNNs, text classification using TF-IDF, and collaborative filtering for recommendation systems. These techniques empower data scientists to leverage big data effectively, creating robust models that can handle complex tasks. In our next session, we will cover troubleshooting techniques and best practices for maintaining Spark applications in production. As we continue our journey through machine learning with Spark, stay tuned for more examples, insights, and of course, a few laughs along. To optimize Spark, understanding the various deployment models is crucial for performance tuning. With Spark becoming an essential tool in big data processing and analytics, selecting the right deployment model can significantly impact the overall efficiency and performance of your applications. In this session, we will discuss several deployment models, focusing on their pros and cons, while demonstrating with examples how to optimize Spark for a variety of use cases. So far, we have learned about leveraging Apache Spark for advanced machine learning techniques that improve data analysis workflows. We covered integrating Spark with external data sources and discussed various techniques, including ensemble methods like random forest, deep learning with CNNs, text classification using TF-IDF, and recommendation systems using collaborative filtering. These methods empower users to effectively manage big data and create robust predictive models. Now we will cover Spark deployment models and how to optimize them for performance. Now let's see how we can set up a Spark cluster in standalone mode, which is the simplest deployment model. We begin by starting the master node using a provided script that initializes the Spark master service. This master node is responsible for managing the cluster resources and coordinating the execution of tasks. Next, we will use another script to start the worker nodes, which will connect to the master node. The command specifies the master's IP address and port, allowing the worker nodes to register themselves and begin executing tasks assigned by the master. It's crucial to replace master IP in the script with the actual IP address of your master node, ensuring proper communication within the cluster. This setup allows you to run Spark applications effectively on multiple machines, which is ideal for larger workloads and enhances the resource allocation process. However, while the standalone mode is user-friendly and straightforward, you must monitor resource metrics closely, as it lacks advanced features like dynamic scaling and scheduling that can improve performance in larger environments. Now let's see how we can submit a Spark job using Apache Mesos as the resource manager. The command spark submit master mesos / mesos master IP 5050 class your main class path to your Spark app jar is specifically designed for this purpose. In this command, we start by invoking Spark Submit, which is the primary tool used to launch Spark applications. The master flag is essential as it specifies the master URL for Mesos, enabling it to manage resources dynamically for our Spark job. You need to replace Mesos master IP with the actual IP address of your Mesos master node to establish a connection. Following that, the class option indicates the main class of your Spark application, where your main class should be substituted with your actual main class name. The final part of the command, path to your Spark app jar, indicates the path to the jar file containing your compiled Spark application code. This structure allows Spark to execute the application, utilizing the resource management capabilities of Mesos effectively. By leveraging this command, you can ensure that your Spark jobs are efficiently managed and can run alongside other frameworks, optimizing resource usage in multi-tenant environments. Now let's explore how to submit a Spark job to run on Hadoop Yarn. The command spark submit master yarn deploy mode cluster class your main class path to your Spark app jar is key to executing your application in the Yarn environment. In this command, the master yarn option indicates that you are directing Spark to utilize Yarn as the resource manager. This allows Spark to benefit from Yarn's robust capabilities in resource allocation and job scheduling, vital for distributed processing. The deploy mode cluster flag specifies that the Spark driver, which coordinates the job, will execute on the Yarn cluster itself rather than on the local machine. This is particularly advantageous for production environments, as it optimizes resource use and enhances fault tolerance. Next, the class your main class parameter identifies the main class of your Spark application. This is where your code execution begins. Lastly, you need to provide the path to your Spark application jar file after the command, which contains all the necessary code and dependencies needed to run the application. By configuring and submitting this command correctly, you set your Spark job up for effective execution within the Yarn framework. Now let's take a look at how we configure the Spark session to optimize its performance for our application. First, we begin by importing the necessary component, Spark Session, from the PySpark SQL module, which serves as the entry point to programming with Spark. Next, we create a new Spark session using Spark Session Builder, which allows us to set various configurations for our Spark application. The appName method is employed to provide a meaningful name to our application. This is helpful for tracking and monitoring purposes. We then set crucial configuration parameters using the config method. For instance, we allocate 4 GB of memory for each executor, which is vital for handling larger datasets efficiently. Additionally, we designate 2 cores per executor to enable concurrent task execution, enhancing the processing speed. Lastly, we provide 2 GB of memory for the driver, ensuring it has sufficient resources to manage the application's orchestration. Finally, we call getOrCreate to either get an existing Spark session or create a new one with the specified configurations. This setup is pivotal because properly tuning these parameters according to your workload can yield significant performance improvements as your Spark applications process data. Now let's see how we can save a data frame in Parquet format, which is an efficient way of storing large datasets. In our example, we use the write method on the DataFrame object, followed by the Parquet function, where we specify the file name for the output data. This method allows Spark to utilize Parquet's optimized storage capabilities, such as columnar storage and built-in compression. As a result, our data is stored in a format that is not only space-efficient, but also conducive to high-performance querying, which can drastically reduce the I/O overhead during data processing. Next, we will implement how to read data back from the Parquet file we just created. This is accomplished using the read method on the Spark session, followed by the Parquet function, and again specifying the file name. When reading in this format, Spark is able to skip unnecessary columns, which means it can load data significantly faster by only accessing the relevant information without deserializing the entire dataset. This selective reading helps improve the performance of Spark applications and is a best practice for working with large datasets in a distributed environment. Now let's see how we can implement a crucial performance optimization technique in Spark by managing the partitioning of our data frame. In Spark, data is distributed across multiple partitions, and the way this data is partitioned can significantly influence the performance of your Spark jobs, particularly during shuffle operations. To optimize the repartitioning process, we can use the repartition method. When we write df equals df for partition 10, we are explicitly instructing Spark to redistribute the data in the data frame df into 10 partitions. This adjustment is beneficial, particularly when the initial partitioning may not align well with the workload, leading to skewed data distribution. Finding the right number of partitions is essential. Too few can lead to resource saturation for some workers, while too many can introduce overhead in managing tasks. By controlling the number of partitions, we enhance overall parallelism and resource utilization, which can dramatically improve job performance. Thus, being judicious about partitioning in Spark is pivotal for efficient data processing within distributed environments. Now let's see how we can implement caching to enhance the performance of our Spark applications. Caching a data frame is a straightforward yet powerful optimization technique that reduces the time required to access data repeatedly used in operations. By using the cache method on a data frame, Spark stores the data in memory, allowing subsequent operations that reference the data frame to access it much faster than recalculating it each time. This is particularly advantageous in scenarios involving iterative computations or when multiple transformations are performed on the same dataset. By retaining the data frame in memory, we achieve significant speedups, leading to more efficient data processing workflows. However, it's crucial to consider that caching occupies memory space on your cluster, so you need to ensure that sufficient resources are available for this feature to be effective without exhausting memory. Monitoring memory usage after implementing caching will help maintain optimal performance and resource allocation, making your Spark applications more responsive and efficient overall. In conclusion, understanding the various Spark deployment models, standalone mode, Apache Mesos, and Hadoop Yarn is essential for optimizing performance as per your application's requirements. Each model offers unique advantages that can significantly impact efficiency and resource management. Additionally, by configuring Spark appropriately, choosing efficient data serialization formats, managing partitioning strategically, and caching data, you can achieve substantial performance improvements. As you venture into building and deploying Spark applications, keep these strategies in mind to make the most out of your big data processing efforts. In our next lesson, we will focus on troubleshooting techniques and best practices for maintaining Spark applications in production. Stay tuned for more insights, examples, and let's continue to deepen our understanding of Apache. Integrating Spark with external tools can greatly amplify its potential in processing and analyzing large datasets. By expanding Spark's capabilities, we can unlock new insights and optimize workflows essential for data-driven decision-making. So far, we learned about the importance of understanding the various deployment models for optimizing Apache Spark's performance. We covered the three primary deployment models: standalone mode, Apache Mesos, and Hadoop Yarn, each with its own advantages and trade-offs. Additionally, we discussed strategies for performance optimization, including configuration settings, efficient data serialization formats, proper data partitioning, and caching techniques. Now we will talk about integrating Spark with external tools, which can enhance its functionality and allow for more advanced data processing and analytics. Now let's see how we can read data stored in HDFS into a Spark data frame. We begin by creating a Spark session, which is essential for any Spark application. The Spark Session Builder method is used to configure the session name, and we call getOrCreate to either fetch an existing session or create a new one if none exists. Next, we'll read a CSV file from HDFS using the Spark read CSV method. The argument provided in this method includes the path to the file, which is specified in the format HDFS//nameNodeIP port/path/to/your/data CSV. This allows Spark to connect to HDFS and access the specified file. Importantly, we set header equals true, indicating that the first row of the CSV contains column names. Additionally, the infer schema equals true option enables Spark to automatically determine the data types of each column based on the content of the CSV. This integration allows Spark to efficiently process large datasets, leveraging Hadoop's distributed storage while taking advantage of Spark's in-memory processing capabilities, thus optimizing data analysis and manipulation workflows. Now let's see how we can connect to a MySQL database using Spark's JDBC capabilities. The first step is to define the JDBC URL, which includes important details like the hostname, port, and database name. This URL serves as the endpoint for connecting your Spark application to the MySQL database. Next, we create a properties dictionary that holds our database access credentials, specifically the username and password for authentication, as well as the JDBC driver class that Spark will use to establish the connection. Having set up the connection information, we can proceed to read data from the specified table in the database. By using the Spark read JDBC function, we pass in the JDBC URL, the target table name, and the properties dictionary that contains our connection credentials. This operation retrieves the data from the relational database into a Spark data frame, enabling us to leverage Spark's robust analytics capabilities on structured data. By integrating relational database access in this manner, we enrich our data processing workflows and can analyze traditional structured data alongside vast big data sets. Now let's see how we can implement the integration of Apache Kafka with Spark for real-time data streaming. First, we begin by creating a Spark session, which serves as the entry point for any Spark application, allowing us to interact with Spark's features. Next, to consume data from a Kafka topic, we set up a streaming data frame using the readStream method. We specify that the data format is Kafka and provide the necessary options such as the Kafka server details and the topic we want to subscribe to. This allows Spark to establish a connection to Kafka and start pulling in data. Then we define a transformation on the incoming data by using the selectExpr method. This method is employed to cast the key and value from Kafka to string types, making it more manageable for processing. Finally, we configure the output of our streaming data frame by using WriteStream. In this case, we choose to display the results in the console for real-time monitoring, and the await termination method ensures that the query runs continuously, allowing us to see live updates. This setup demonstrates how effectively Spark can process data streams in real time, opening opportunities for dynamic analysis and event detection. Now let's implement the following code to integrate TensorFlow with Spark for efficient machine learning model training. We start by importing the necessary libraries, TensorFlow for building our model and Spark session from PySpark for handling our data operations. After establishing a Spark session with the name TensorFlow integration, we proceed to load our dataset into a Spark DataFrame using the read CSV function. This DataFrame will serve as our primary data structure for machine learning tasks. Once the data is loaded, we convert the Spark DataFrame to a Pandas DataFrame, which is compatible with TensorFlow. This conversion allows us to utilize TensorFlow's data handling functions seamlessly. We then create a TensorFlow dataset by using dataset from tensor slices, which prepares our features and labels for the modeling process. Next, we configure this dataset into batches of 32 to optimize the training process. Following the data preparation, we define a sequential Keras model that consists of 2 layers, an input layer with 64 neurons using the RayLU activation function and an output layer. The model is then compiled with the Atom optimizer and a mean-squared error loss function, which is suitable for regression tasks. Finally, we train the model on our dataset for 10 epochs, allowing it to learn from the input features and corresponding labels. This integration enhances our ability to build sophisticated models, leveraging Spark's data processing capabilities, while utilizing TensorFlow for machine learning. Now let's implement the following code to integrate Spark with Apache Hive. We begin by importing the necessary Spark session class, which is essential for creating a Spark session. To interact with Hive, we will set up a Spark session that has Hive support enabled. This is achieved by using the builder method of Spark session, where we specify an application name, in this case, Hive integration. By calling the enable Hive support method, we allow our Spark session to access Hive's capabilities. This means you can run SQL queries directly against Hive tables, which is particularly useful when dealing with large volumes of structured data. Once the Spark session is created with the getOrCreate method, you can execute SQL queries. In our example, we query a Hive table using the SQL method, selecting all records from a specified table where a certain condition is met. This ability to use familiar SQL syntax to fetch data from Hive not only streamlines data analysis, but also leverages Spark's powerful processing engine, allowing you to work with big data seamlessly. Now let's see how we can implement data visualization using Matplotlib after processing our data with Spark. First, we import the necessary libraries, including Pandas for data manipulation and Matplotlib for creating visualizations. The next step involves converting the Spark data frame into a Pandas data frame. This is important because Pandas provides a more straightforward interface for dealing with smaller datasets and facilitates seamless integration with Matplotlib. Once we have our data in a Pandas data frame format, we can easily create visualizations. In this particular example, we focus on creating a histogram of a specific column, which allows us to observe the distribution of values within that column. We specify the number of bins for the histogram, which helps to detail how frequently each value range occurs. Subsequently, we set the title for the histogram and label the x-axis and y-axis to clarify what each represents. Finally, we invoke the show function to render the histogram on the screen, effectively allowing us to convey our data insights visually. This step of visualization enhances our understanding and enables effective communication of findings based on the processed data. In summary, integrating Spark with external tools enhances its functionality and makes it a powerful option for data processing and analytics. From leveraging Hadoop stability to interacting with real-time data streams through Kafka, integrating SQL databases, or utilizing machine learning frameworks like TensorFlow, Spark proves to be flexible and versatile in handling various data challenges. Integrating Spark with Hive for SQL queries opens up structured data analysis, while drawing on visualization libraries makes it easier to represent your findings visually. The possibilities are vast when you integrate Spark with the right tools, enhancing your ability to process data effectively and extract insights. As we continue in our learning, always remember that the goal of integrating with these external tools is to augment Spark's capabilities, enabling you to turn your data into actionable insights efficiently. In our next lesson, we will explore best practices for troubleshooting Spark applications in production, ensuring that you can maintain those integrations smoothly and effectively. Stay tuned for more tips and tricks on navigating the world of Apache. In this final section, we will do a project challenge to apply what we have learned so far. The objective of this challenge is to leverage your PySpark skills on a dataset of your choice, whether it be related to sales data, social media interactions, or financial stocks, to conduct a thorough analysis. You'll begin by loading your dataset into a PySpark DataFrame and performing exploratory data analysis to gain insights into its structure. Next, you will clean the data by addressing any missing values or inconsistencies before transforming it to create new columns or aggregate data as needed. With your data prepared, you will conduct an analysis focused on your specific questions or hypotheses, such as correlations or trends, and visualize your findings using appropriate graphs or charts. Finally, you will document your methodology, insights, and recommendations in a clear report. This project not only allows you to demonstrate your understanding of PySpark, but also challenges you to think critically about data analysis. You can find the details for the final project in the GitHub repository linked in the description.